Australia is a nation of creators, aviators, protectors and innovators. From aviation's first light to the dawn of the jet age and beyond, at Boeing, we're building the future together here in Australia. Inspiring those in pursuit of new frontiers, connecting, protecting and exploring our region and the world. Home to the broadest aerospace portfolio in Australian industry, powered by talented, dedicated and diverse teammates. Delivering manufacturing excellence, building composite aircraft parts for the world's most efficient airplanes, using advanced robotics, materials and digital technologies. Never compromising on safety or quality, always focused on sustainability. Solving tomorrow's problems today with Australia's leading researchers, scientists and universities. Developing new military platforms and communications networks and helping ensure they are always mission ready. Keeping customers airborne by providing the services they require. We stand shoulder to shoulder with Australians during natural disasters, on the front line and in peacetime. We support veterans and our community, and we nurture the next generation of aviators to excite, to be bold. Boeing Australia. Made in Australia, by Australians, for the world.
Okay, are you ready? The first university to admit women, 2 Nobel Prizes, then another, then a couple more, 12 knighthoods, 22 Olympians, a pack of COVID-sniffing canines, Australia's first female Prime Minister. Finally, treatments for diseases and other scary things, the first female Queen's Counsel, Supreme Court Judge and State Governor, all in one, first in the family with a degree, a black belt, a robot. First Aussie to walk in space, helped detect gravitational waves, made lots of babies, world top 100 in all this stuff. Launched a satellite, revived lost languages, home to 1,600 brainiacs, and a winery, all in the heart of Australia's most livable city. So, what's next? Make history at the University of Adelaide.
Good morning everyone and welcome to day 2 of the Australian Rover Challenge at the 3rd instalment this year in 2023. My name is Daniel Ricardo and I'll be your MC/commentator for today. So today's task is the excavation and construction task, which is task number 2 out of 4. So rovers from 8 different teams from around Australia, including Poland, will have to excavate some debris, some regolith from the surface, deposit it in a hopper, clear some debris that's out on the field, and then deploy a pavement or a road from the rover that the rover will then drive over to show or demonstrate that it can construct infrastructure on the surface. So up first, we've got RMIT, so the RMIT rover team from Melbourne. Their start time on the field is 10 o'clock. So the task time is about 40 minutes and there are 100 available points up for grabs. So first there'll be 5 points for the rover descending down the ramp. This is to showcase that the rover can move, can be remotely controlled and operated. Then there will be 20 points available and the rovers can complete this in any sequence. 20 points available for clearing the debris out there between the valley. There will be 35 points for constructing the surface. So the rover teams, the university rover teams, have designed and built their own deployable pavers, a mechanism to showcase dust mitigation. And the purpose for this is the lunar surface is covered by a really fine, extremely jagged, extremely hazardous soil called regolith. And we call it regolith because it is an extraterrestrial soil that covers the moon, it covers Mars, it covers extraterrestrial bodies like comets and asteroids. And it is unique because it is essentially crushed rock that has been pulverized over billions of years by meteorites. And once you pulverize rocks in that manner, it becomes extremely jagged, extremely sort of like asbestos. So if you were to travel out on the moon, inhale some of the dust that gets out there, you would get silicosis because it's crushed rock, and rock are made of silicates. So this is a huge issue, as any mechanical mechanisms, moving parts as part of a rover, as part of any sort of moving infrastructure on the surface of the moon or Mars, would have to compensate for the amount of dust that gets into those joints. Because as you're moving apart, if there's dust that gets in there, it acts like jagged glass. It causes a lot of wear, a lot of abrasion. And then on the flip side, as you're sending humans to the surface, it's a huge hazard to their health, because this is one thing the Apollo astronauts noted again and again in all their transcripts, their audio transcripts and some of the recordings. You'll note, if you ever want to go on YouTube or on NASA's website, you can listen to the actual recordings of the Apollo astronauts beaming back to Earth. They all noted just how hazardous, just how frustrating it is to deal with the dust that coats everything. It coats their visors, it gets into the gaskets of their gloves and their spacesuits. It gets into the lander where they live and breathe, and it just gets everywhere. And because couldn't end up seeing by the end of the Apollo mission, because they kept scratching their visors trying to get it off, and you can't get it off because it is so fine-grained, there's no atmosphere, so it's electrostatically charged, it just sticks to everything. So if you're listening, or for the students out there, and you have some novel solutions of how to mitigate the dust issue, then you've got the golden ticket to one of the biggest issues that is facing all space agencies around the world and private space companies. So that is the construction task. And last but not least, and you can complete these tasks in any order as well, is the regolith, is the excavation and deposition activity. So you can see out on the field the square pile of dirt just to the left of the post-processing plant. Behind the antenna, you can see on the screen, we've got a pile of regolith that we've sourced, and it is the rover's job to try and excavate material from this pile and then deposit it into a hopper on the processing plant. And this is to demonstrate the excavation, the transport, and the deposition of regolith on the lunar surface. And this is exactly what the Australian Trailblazer mission, or the Australian Lunar Rover, will have to do as part of its remit, as part of its mission, as Australia's role in the Moon to Mars program. And this is NASA's plan to send humans back to the moon, the first woman back to the surface of the moon in a few years, and then to progress, to send humanity onwards to Mars. And this time we're going there to stay. So the Australian Rover Challenge, the whole purpose of it is to provide students with the opportunity to design, develop, build and test rovers as part of a simulated lunar mission. And this gives you a lot of opportunities that you can't really get anywhere else. Unique opportunities like not only designing a robotic system, which draws upon expertise from almost every faculty within a university, from engineering, so you've got electrical, software, mechanical, you've got people from science, so I'm a geologist myself. You need people from the biochemical faculties as well, in terms of understanding the material science. You've got people from humanities, you've got people from business, economics, so really drawing upon almost every faculty to showcase that space is for everyone. As we transition into space, it's humanity transitioning to space, and you need to bring everyone with you. So as we progress today, you'll see a suite of different teams, rover teams from around Australia, from several different states, and we cannot wait to showcase some of the amazing work that these students have been putting into their rovers night in, night out, getting much less sleep than they should, to showcase that Australia is ready. Australia is ready to commit and contribute to the space industry and showcase our expertise in remote operations, in autonomous traversal, autonomous use of rovers, of trucks, and to try and showcase a lot of our expertise in mining and sustainable mining. So one of the big issues that we face as we transition into space is the requirement for using resources, fuel for rockets, fuel for rovers, growing food, getting water, getting oxygen to keep humans alive and to keep them alive for longer, and to make sure that they're happy out in space. And one thing that you can do is the in situ resource utilization, which is ISRU. It's a big buzz term that everyone's using. And essentially, it just means the use of resources in space so that you don't have to ship everything up into space with you, because everything has mass, and if you want to send something to space, it's expensive, and the more it weighs, the more expensive it is. So if you can use things in space to create a circular economy, it's a lot less expensive, it's a lot safer as you're sending less rockets, creating less debris, and it's a lot simpler, and it's quite exciting. So one of the challenges that, or one of the unique opportunities that the lunar surface presents us is the regolith that coats the surface contains a lot of essential things that we can utilize to develop different materials for use in space. So you can extract metals from the regolith by heating it up. You can yield or also extract volatiles like hydrogen and oxygen, which you can combine to create water for growing food, growing crops, for drinking water. You can use the oxygen for breathing. And you can use the metal for the production of wires and steels in space so that you can create other things like rovers or more infrastructure. Or you can use the remnant or the leftover regolith, the dried pieces of rock, for construction, because the lunar surface has no atmosphere, it has no magnetic field, or a little magnetic field. And this means that extremely hazardous things like ultraviolet radiation, cosmic gamma rays, radiation from the sun, micrometeorites, the lack of any atmosphere means that there's no oxygen that you can breathe. So all these things make living on the surface as a human extremely dangerous, even for short periods of time. So the question then is, how do you keep them alive? How do you keep them safe? And how do you do that for long periods of time? And rather than sending up huge, thick pieces of protective habitats, why not just use the abundant regolith that is available on the surface? So you can actually insulate a human from a lot of these hazards by just using on the order of about a meter or several meters of regolith, depending how dense you pack it. And the brilliant thing is that if you were to just dig up some regolith, extract the metals, extract the volatiles, use the remnant regolith to make some bricks, make a habitat, you're on the verge or in the process of making a circular, sustainable base on the moon. And these are the challenges that many of the student participants today may face as they progress onwards into the space industry. And we cannot wait for them, or we cannot wait to support them in that journey. So again, just to reiterate, coming up on 10 minutes now, the start time for the excavation and construction task for the RMI team from Melbourne has just started. So they've got a 40-minute window in which to complete the 3 different activities. So as a rover team, they're allowed to start at any time. However, they must complete the activity within their 40-minute slot. So one thing that participants who are not familiar with rovers is that it is not simply driving an RC car. It's not as simple as plugging in a Xbox controller or the like, and then pressing go and going forward. These are entirely designed, built, tested, and developed by undergraduate students in their spare time as they're also studying. So things may not often work. So the view up on the live stream right now is the live stream coming down from the base station. Now this base station where the rover live stream will feed from the rover's cameras and the input sensors are streamed to the group or the division of the team in the base station. Reiterate the base station feed, so the teams are split up into 2 different groups, the field team and the base station team. And the base station team's job is to rover during the task, and the field team's job is to make sure that nothing goes wrong out in the field. There is, once the task starts, there is no communication allowed between the teams, so this is simulating the difference. So if you're deploying a rover to the lunar surface, you can't simply just be out there controlling it like an RC car. You're operating it back on Earth, often with a delay, because the moon is far away, and that delay is about 4 or so minutes. So unfortunately, we don't implement a delay because things are enough. But the base station you can see there with some wooden trestle tables is a tent, and it is actually quite luxurious on the order of Rover Challenge competitions. So there's another Rover Challenge out in the US, the University Rover Challenge. The participants just got selected as of yesterday, so congratulations to the winning 36 participant teams that will go on to at the URC. But if you're competing at the URC, your base station is the back of a U-Haul truck out in the desert, so quite a difference. So the base station team, you can see right now, are trying to get their visual sync. You can see the heads virtual reality goggles. The different utilize different ways of controlling the rover. So often they have video camera streams. Depending on the bandwidth, you can also have stills, so the rover takes intermittent pictures. And some other teams have virtual reality heads-up goggles so that as the operator is driving the rover, they get to look around as if their head is on the rover on a pivot. Different approaches have different advantages and different limitations. And this is one of the beautiful things about the Rover Challenge, is that there's no right or wrong answer. Students can approach the task or any task and design their rovers in any way they want. It's quite innovative, it's novel, it gives you a lot of creative freedom that you can't really get in other challenges. And this is one of the beautiful things coming down as a participant and having competed in Rover Challenges myself, is that the beautiful thing is meeting teams from around different countries to see how they approach the same task. How many wheels do you have? Do you have 4? Do you have 6? Do they have independent individual pivoting steering? How many linkages, how many degrees of freedom is your robotic arm? Do you even use a robotic arm? How do you control your rover? How do you power your rover? How big is your rover? What dimensions? These are all the things that enable the rovers to be extremely different, extremely varied, I think extremely beautiful as well, because you can have some gorgeous color schemes on it. But it also opens up the opportunity that when they go on to industry, they've had the opportunity to test out things. There's no strict design parameters for a rover. And this is the thing, is that no one really knows the correct answer of how to build a rover for the moon, because we've only been there a few times, particularly with a rover. And that is one of the exciting things about Artemis. So the sister to the Apollo program is NASA's Artemis program, which will be sending the first woman and the next man onwards to the moon, to the lunar surface to stay, later in the 2020s. So for those tuning in on the live stream and those watching as spectators out on the field, welcome to the 2023, the third installment of the Australian Rover Challenge, where we're hosting 8 teams from around Australia, and welcome to the team attending, our first international team attending from Poland. And right now you can see the RMIT Rover team up on the lander. Their start time for the excavation and construction task, the second task out of 4 tasks available for the overall challenge. Their start time was at 10. They've got 40 minutes in which to complete the 3 different activities. One of them is the debris clearing, so the rover needs to clear several pieces of debris out on the field. The rover needs to excavate some regolith, which is extraterrestrial soil, or essentially extremely fine, jagged, crushed pieces of rock, deposit it in a hopper, and then, last but not least, the deployment of pavers that they've made, tiles, to cover a approximately 1.2 by 2 meter area. And this is to showcase the rover deploying infrastructure on the moon by itself. And by infrastructure, I mean a road. So the rover will be building its own road, and the purpose of this is to try and demonstrate a dust mitigation technique. And what that means is the lunar surface is covered by an extremely fine-grained material, which is regolith, where its dust, its fine-grained fraction, can levitate off the surface of the moon up to about 10 meters and poses a serious risk to any human out on the surface or any mechanical mechanism like a moving rover part. And this dust gets kicked up by any movement, stays levitated for hours to days, and was the number one issue that the Apollo astronauts noted after their several trips to the moon, is that it gets on everything. And once it gets there, it stays there. It scratches everything. It gets into your lungs if you're unfortunate enough to breathe it in. And it stays in your lungs like jagged pieces of glass, tearing up the tissue within your lungs, in the lower portion of the lungs. And the purpose of this task, this excavation and construction task, is to try and highlight the amazing talent that we've got around the world, particularly growing here very rapidly in Australia, for the design and operation of autonomous or semi-autonomous rovers with the capability of performing foundation services. So a foundation services rover is the exact rover that the Australian Space Agency, together with NASA as part of their Moon to Mars program, will be sending to the moon as part of Australia's first significant mission to the lunar surface, where we'll be deploying a foundation services rover. And the winners of this grant, the first 2 winning consortia, were announced only a few days ago. So congratulations to everyone involved in the challenge, and I can't wait to see what amazing rovers are developed and then sent to the moon to inspire the next wave of Australian students to progress into space. Because, as I always say, you can't be what you can't see. So the moment that we start getting some significant missions and payloads out into space, getting some awareness of the amazing and dedicated work of individuals across Australia working on these rovers, that will just showcase to students around Australia, hey, I can also do that. I want to do that. Those tuning in, I'd just like to reiterate that the operation of these rovers is not as simple as driving an RC car. You can't just turn it on, push forward on your controller and go. These are entirely designed, built, tested and operated by undergraduate university students, also juggling time with studies and often part-time work as well. And no one teaches you how to make a rover in university. So everything you see today, or you see tomorrow, or you will see tomorrow, is entirely done by these students in their spare time on a volunteer basis, and that they've taught themselves. So the operation of this rover is done remotely via a live feed, so often via 2.4, 5 gigahertz communications, and you can see the black antenna on the back, that rear end of the rover. They've also got the robotic arm, which is moving right now, which looks like about 6 degrees of freedom, and that just means there are, you can think of it like a shoulder joint, an elbow joint, a wrist joint, and that little end effector, and each axis of movement or rotation is a degree of freedom. And again, these are highly complex systems, entirely researched and developed by undergraduate students, so every time you see something moving and working, it is a huge milestone, because it's one thing to work in a lab, it's another thing entirely for you to ship your rover interstate or often overseas, deploy it out under competition conditions, and for it to work as expected, which often doesn't happen. And for all the participants here today, I'd just like to reiterate or remind you of the Make History on the maths lawns in front of the Bar Smith Library. It'll be at 5:30 p.m. tonight. It is a free event. You can register online. Doors open at 5. And it looks like the rover has taken its first steps with one wheel just about over the ramp. To get 5 points for the initial activity, which is the descent down the ramp, all wheels need to get off the ramp and need to make full contact with the sand. And it looks like it's in a precarious situation. So currently is perched up on a precarious angle off the lander. And this is just highlighting some of the issues that you may encounter as you're deploying your rover down the lander. And this is something that has been highly tested and highly researched by many space agencies around the world. If you'd like to look at some amazing videos, you can watch Viper, which is NASA's lunar rover that they're sending to the South Pole in the next few years, hopefully, maybe even later this year. You can watch the deployment mechanism off the lander developed by a private company in the US. And a lot of work goes into those first few steps. Now, for reference, the base station are allowed to call an intervention, where the task time is paused and the team are allowed to make some basic fixes, while the field team are allowed to hit the E-stop, the emergency stop. And this ceases all power to the rover and ceases the task. And the task today for the RMIT rover team is the excavation and construction to task, worth 100 points out of an available 500 points for the overall challenge, consisting of 100 points from the CDR and the SAR submissions, the Critical Design Review and the System Acceptance Review, which are written documents, which are very common in any systems engineering mission as part of a space project. And these are documents that many individuals have written as part of many payloads into space, and we're giving students an incredible opportunity to write reports as part of a mission that they're developing. And this is the exact experience that they will be expected to complete if/when they decide to progress into the space industry. It looks like the base station team is called an intervention. So there will be some basic maintenance on the rover to make sure that everything is good to go. And just a reminder, this is the 10:21, so we're about 21 minutes into a 40-minute time slot for the excavation and construction task. The task has 3 different activities, one of them being the debris clearing, which is there are some debris placed out in the field, and it is the rover's job to go clear it out. They will get points for each piece cleared. Then the rover must go and excavate regolith, or the extraterrestrial soil, from the surface and deposit it in a hopper. They get points for the amount of dirt that they place in the hopper. And this is from the RAS, the Regolith Acquisition Zone, and this is the exact task that the lunar rover, as part of the Trailblazer mission, a fully Australian mission to the lunar surface using a rover, will have to complete in the next couple of years. And this is really critical as we're getting students involved with the exact operation of a rover on the lunar surface, doing the exact tasks that a fully Australian mission will have to do. So we're creating an excellent talent pool here of students ready to go for that mission and for many other missions as Australia grows as a nation into the rapidly expanding international space industry. And the last but not least activity for this task is the construction task, and you'll notice the square smiley face out on the field, and this is designating an area where the rover has to deploy its own road, and this is a road made up of interconnected pavers, or pre-connected systems sometimes. And this is to try and get the rover building its own infrastructure, and that's building a road on the surface to try and stop the kick-up of dust as the rover drives around. And this is a real-world and quite a significant issue that has yet to be addressed by some of the best researchers from around the world. And we're trying to showcase that undergraduates can do it. Anyone with passion for space exploration and talent and a drive can create solutions and deploy them out here at the Australian Rover Challenge on this simulated lunar surface to show that, hey, we can do this. During this intervention, the base station team cannot communicate the orientation or the position of the rover, and this is to just try and simulate that once your rover's out there on the moon, it's on the moon. You can't send out a technician to simply fix it, and this is a real-world scenario that will/may occur if things go wrong. And let's see if the RMIT rover team can push through with just about 16 minutes left on the clock. 5 points up for grab for descending down the ramp, and this is just as long as all 6 wheels make contact with the ground. up on the live stream now, you can see the RMIT base station team. So this is the team comprised of students operating the rover. And there is also a contingent of students out here on the field comprising the field team. And you can see the way that this team controls their rover is using a virtual reality headset, enabling the operator to have up to about 360 degrees field of view as if you're controlling the rover first person. And again, this is one of the sensational aspects of the Australian Rover Challenge, is that every team has a different rover, different communications protocol, different way of operating, different way of testing, different way of redeploying. And one of the great things is that we get to witness some incredibly novel and innovative solutions to common problems, such as, or simply as, how do you drive a rover? Reiterate that later today, out here, for all the rover participants, there will be from 10 till 1 Animals Anonymous bringing down some native Australian wildlife to interact with, including but not limited to a little crocodile, some snakes, some native birds, and last but not least, a beautiful little quokka named Queenie. With just about 11 minutes left on the clock for the RMIT rover team as part of the second out of 4 tasks for the Australian Rover Challenge, the excavation and construction task. There are about 100 points available for this task, broken down into 3 different activities: the debris clearing, the regolith acquisition and transport, and the construction task. Here on the lunar surface, on the pitch, it is quite windy, but on the lunar surface with no atmosphere, you have no wind, no rain. So the only weathering process is that of the intense radiation from the sun and from interstellar objects, such as micrometeorites, which are tiny or can be up to, several meters or kilometers big, depending on the size of the object. But pieces of rock hurtling through space only to land with kilometer per second trajectories into the lunar surface, acting like little explosions or little hammers, crushing up, pulverizing the lunar surface, creating the fine-grained extraterrestrial soil that we call regolith. This material is composed of rocks, silicates, and sometimes glass, depending on how quickly it cools. And these particles you can think of them as little tiny jagged pieces of rock that get absolutely everywhere, and because there's no atmosphere, they can become electrostatically charged, which just means as the solar radiation hits the surface of the moon, it can become positively or negatively charged, depending if it's daytime or nighttime. And on the moon, daytime and nighttime takes about a month, because that is the time for a lunar cycle to happen. So you have daytime, pure daytime for about a month, pure nighttime for about also a month. And this raises many issues of how do you control your rover with time? It gets cold out there on the surface. There's no atmosphere. There's nothing to conduct the heat away. You can only radiate. there's no convection. And this just means that if you've got a rover out there on the lunar surface exposed to direct sunlight, depending where you are on the surface, if you're at the equator, the surface temperature can get up to about 400 degrees Kelvin, several hundred degrees centigrade. If you're a rover or a human, that's pretty hot. On the flip side, as soon as the sun sets, it gets cold really quickly, down to on the order of less than 100 Kelvin, so minus several hundred degrees. And this poses another risk. How do you keep your electronics warm? Things break when it gets cold. So not only are you designing a rover or a human life support system for radiation, micrometeorite particles, extreme temperature, the lack of atmosphere, huge vacuum, you are also designing for extreme temperatures where it gets extremely hot, which pose a risk to your electronics or your humans, and it gets extremely cold, which is on the flip side. So you're designing something that has to be extremely robust and independent, because when things break on the lunar surface, you can't simply send out a technician to go fix it. And another interesting fact, because of that diurnal cycle, so the sunrise and sunset on the moon, and because of the lack of atmosphere and the charging of particles, you have this wave as the moon rotates on its axis. The dust levitates up to 10 meters off the surface, and you can see some sensational notes from some of the Apollo astronauts describing this sunset, this silhouette across the horizon as the sunrise, grazed across the surface of the horizon, illuminated all the dust, and created a gorgeous, never before seen sunrise or sunset on the lunar surface. And later, in the next couple of years, humans will set their eyes on that scene once again as part of NASA's Artemis program, sending the first woman and next man onto the surface, this time to stay with several resupply missions and human missions to the surface as part of NASA's Artemis mission, with the broader goal of sending humans onwards to Mars. Screen, you can see it is 10:34, just about 6 minutes remaining on the clock, with the task time for RMIT's excavation and construction task ending at 10:40. 5 points up for grab for descending down the ramp, and this is just highlighting the extreme technical difficulties with building a rover by scratch, by undergraduate students who are also working and studying, shipping over the rover from interstate, and getting it all to work under competition conditions out here in gorgeous University of Adelaide math lawn in front of the Bar Smith Library. So operating a rover, multiple different things have to work in synergy for the rover to be operable and to complete its task. Not only do you have to design our communication systems, it has to communicate back to the antenna wirelessly, often on 2.4 or 5 gigahertz. These are the publicly available bands that students can use. You also need to make sure that that connection conveys its instructions from the base station team, who you can see up on the live stream right now, conveyed the instructions of their input, so go forward, backwards, left, right, move the robotic arm, deploy different subsystems. The mechanical system and the electrical system, together with the software developed by these students, needs to work on the rover. And sometimes you can have issues in terms of wheels, motors torquing out, receiving too much or too little power. You can have sometimes even broken traces on the PCB, so the electrical boards in the rover, which is something that me and my team struggled with when we competed at the University Rover Challenge. Our wheels were driving backwards when they're meant to be driving forwards because of a broken electrical trace. And with 4 minutes left on the clock, let's see if the field team and the base station team can troubleshoot to figure out what, out of all the different complex systems on their rover, is going wrong. And again, just to iterate, this is the second out of 4 available tasks. So if this team doesn't manage to get any points for this task, there are still many points up for grabs as part of the Australian Rover Challenge, which is here to showcase some of the amazing work these students are doing. And with every year, these rovers get better and better, and I am awestruck of how quickly things have grown and changed since the first installment of the Rover Challenge back in 2021, which we launched just after COVID, which was quite interesting. We only had 3 Australian teams. Now we've got on the order of about 8 with an international competitor, and we will continue to grow. We're going to get more teams, more students involved. The RMIT Rover team have called the end of the excavation and construction task. So can we get a huge round of applause, please? Phenomenal effort. So up next on the...
Okay, are you ready? The first university to admit women, 2 Nobel Prizes, then another, then a couple more, 12 knighthoods, 22 Olympians, a pack of COVID-sniffing canines, Australia's first female Prime Minister. Finally, treatments for diseases and other scary things. The first female Queen's Counsel, Supreme Court Judge, and State Governor, all in one. First in the family with a degree, a black belt, a robot. First Aussie to walk in space. Helped detect gravitational waves. Made lots of babies. World top 100 in all. This stuff. Launched a satellite, revived lost languages, home to 1,600 brainiacs, and a winery, all in the heart of Australia's most livable city. So, what's next? Make history at the University of Adelaide.
And welcome back. We've got the Monash University Nova Rover team from Melbourne, Victoria, up on the lander with their hot pink rover named Waratah. And the hot pink is meant to symbolize the engagement or the raise of the discussion of getting more females into STEM, making sure that the workforce that we're sending into space and the ground infrastructure team helping those teams is comprised of the very best individuals from every background, every culture, every discipline, to make sure that the infrastructure and humans that we send up into space are secure, are safe, and function as intended. So up on the screen, you can see the current total score and first place podium sitters currently. Monash Nova Rover team with a score of 176.1 points, and this is comprised of their performance from yesterday's task, the Australian Space Agency post-landing task, worth a total of 100 points, together with their submissions as part of the critical design review and system acceptance review, together worth another 100 points. And these are formal documents that the teams submit to us, the judges, to verify that their designs meet the criteria of the challenge. And these are documents that they, if they do decide to work onwards onto missions into space, are very common and expected as part of the systems engineering and project management of a mission throughout the development of a satellite or a rover or an instrument. And up on the screen you can see the scoreboard, the current scoreboard, the tally of the 8 Australian and international teams, undergraduate teams from universities now around the world. And as the teams perform their tasks, we will continue to update this leaderboard. And the total available points is about 500. So 100 for those formal submissions, and then 100 points for each of the 4 tasks. Now you can see the base station team of the Monash Nova Rover team, comprising what looks like 6 individuals. And these include, or not limited to, people operating the rover, people planning the strategy of what they do and how they do it, people managing the different subsystems on the rover. So each team has a novel and often entirely different approach for how they complete or intend to complete this task. And often rover teams have to design and develop all of their own control mechanisms. So many teams use the joysticks, which you can see out there on the table. So if you've ever done flight sim or flight simulator, you know these joysticks very well. Some teams go as far as to create their own interface, which are basically suitcases or pelican cases, which they've fitted out with their own control mechanism with switches, knobs and dials, which is an incredible display of designing a solution to a practical issue, which is how do you control a rover? There's no right or wrong answer. And again, the amazing thing about the Australian Rover Challenge is that we get to witness all the teams' different approaches to all these fundamental questions, such as, how big is your rover? How much does it weigh? How many wheels do you have? How do you control those wheels? What about that subsystem for clearing debris or picking up regolith? Do you use a scoop, like you can see up on the screen right now? Do you use a drill? Do you use some other mechanism? Hot pink wheels, the fins that coat them are called grousers, and they give those wheels the ability to get traction in this loose soil that covers the arena right now. And another question is, when you're designing a wheel, how big is your wheel in terms of diameter? How wide is your wheel? How big are those grousers? What shape are they? Is your wheel solid? Is it hollow? So NASA spent several years in the design and development of their rover wheels for the Mars Curiosity and Mars 2020, which is called the Perseverance rover. And the development of those wheels are really the fundamental backbone of how that rover interacts with the surface, because it is the only, or sometimes the sole point of contact. And often those wheels over several hundred sols, which is a Martian day, that get degraded as they're driving into jagged, hard rock. Sometimes they shatter, sometimes they break, sometimes they pick up little passengers. So if you type into Google, the passenger rock, you'll see a little pet rock that got caught in one of the rover wheels as it was driving across the Martian surface. And you can see, maybe up on the screen right now, some of the sand that's caught in the Monash Nova Rover team's wheels. Solutions that the rover team is attempting this year is the use of individual pivot steering, so that almost square bracket connecting to the wheels. Each wheel can pivot on its own axis, enabling the rover to strafe across 2 degrees of freedom. So unlike your car, which has a stuck skid steering, so you turn the wheel and both wheels, you turn the steering wheel and both wheels turn together and you have to reverse in an arc. This rover can pivot individual wheels on an axis and drive directly left or directly right, and can turn in very much tighter arcs and pivot on the spot. However, this is no simple feat. And as several other rover teams have demonstrated, that there is no right or wrong answer in how you drive your rover, how you design your suspension, or how you design your wheels. The novel thing is that we get to see how each of these designs play out. And as it traverses the often extremely dangerous and complex lunar surface, it encounters things like cliffs, valleys, hills, rocks. And of course, the rover can't climb over all these things. It needs to consider risk mitigation. Sometimes the shortest path is not the safest path. And not only do the rover operators need to understand that, the rover itself needs to understand that as part of its semi-autonomous system, which is part of the mapping and autonomous task later on Sunday, where the rovers will be driving semi-autonomously and sometimes autonomously around the course as they navigate through several obstacles and map the arena, which addresses a really fundamental question of the moon doesn't have GPS. We don't really know where things are unless we map them. And then, what are you mapping against? What is your reference point? Where is coordinate 00? And it looks like the rover is descending down the ramp at 10:46. So the start time for the task was 10:45, so they're making great time today. And as those back wheels touch the surface, they will get the first 5 points for descending the ramp. And the 3 activities up for grabs for the rover include the regolith excavation and deposition activity, the debris clearing and construction. So up for grabs is the construction task worth 35 points, where that roll of 3D printed pavers on fabric will be used to deploy a road that the rover will then drive over. And the purpose of this task is to show that rovers can construct infrastructure on the surface to try and address the problem of dust mitigation, or dust on the lunar surface. And the goal of this task is to cover that square area highlighted in blue with pavers that the teams have designed and built themselves. And this is quite a tricky challenge because you're designing against the constraints of covering that area, but also trying to minimize the mass and the dimensions of your pavers, because sending mass into space is expensive, and we want to challenge the teams of thinking of novel solutions of how do you cover an area on the surface and make complete contact? How do you keep it lightweight? How do you deploy those mechanisms? So each rover will have a different approach of deploying their pavers. Little strafe as the rover's trying to line up itself to deploy those pavers onto that surface. And again, this is just highlighting some of the advantages of pivot steering and the limitations that may happen with the control. So Monash has started at 10:45 with the finish time of this task at 11:25. 40 minutes on the clock with 35 points up for grab for construction, 20 points for debris clearing, and 40 points for excavation and deposition. Fun fact for you, bit of history. When I visited NASA Ames as part of an internship, I was working on a rover similar to this with pivot steering on each of its wheels, and only now can I fully appreciate the complexity of pivot steering and getting movement to work the way you want it to. And also highlighting the fact that although sometimes NASA do engineer the best things, when I was helping putting on some of the wheels designed by JPL onto the rover at Ames, they didn't measure the clearance and the rover wheel just hit the chassis and got stuck. And that was an issue that we faced when we were building our rover back in 2018. So really, even the simplest mistakes can be made by everyone from undergraduate students all the way to professional rover developers at NASA, and just highlighting the difficulties of building and operating a rover, and highlighting how sometimes things work, sometimes they don't. It's all about how do you recover, how do you learn from your mistakes and improve with each iterative design. So as the rover attempts this construction task, its activity is to deploy that roll of pavers that the students have designed and built into that allocated little bay with a smiley face, of course. And this is to demonstrate the rover building its own road, whereby it will drive over its pavers to demonstrate that A, it can work, B, it doesn't move, and C, that the deployment mechanism fully worked. And one of the things that the team has to think about, in addition to all the complexities of designing their system and bringing it here to operate, is the game theory of how long do we spend on each task? Which task is worth the most points? Which task can we complete within the allocated time? Where are the tasks in relation to the layout of the arena? The end of the task time is 11:25, and it looks like they're attempting their first activity worth up to 35 points as the rover lays down its sheet of pavers, 3D printed onto fabric, it looks like, as they attempt to cover the surface, the allocated bay, with pavers, whereby the rover will then drive over its pavers and with the remaining time attempt the other activities, the debris clearing worth 20 points and the excavation deposition activity worth 40 points. Let's see how they go with this one. And for those new tuning into the live stream and the new spectators out here on the pitch, welcome to the third installment of the Australian Rover Challenge. Right now up on the screen you can see the Monash Nova Rover team. Looks like they've just completed their first activity, the construction task worth a total of 35 points. And this task is to try and get some dust mitigation on the lunar surface for the rover to build its own road. And why, you may ask? Because the surface of the moon is covered by dust and tiny fragments of crushed rock called regolith, and this stuff gets everywhere on the surface of the visors of the Apollo astronauts, in the seals of their suit, preventing complete seal and prevention of, the atmospheric oxygen inside their suits from escaping, preventing rover wheels, mechanical moving parts like rover arms from operating over long periods of time, as the more dust gets in there, the more wear and abrasion happens, as well as sometimes getting into the Apollo lander module, getting onto all their clothes. And this is one of the major issues that the Apollo astronauts identified to the success of future missions to the moon is the dust gets everywhere. And today's challenge is trying to get undergraduate students to solve this issue. And it looks like the Monash Nova Rover team might have done just that with about 30 minutes left on the clock. And this highlights another important issue is once you design your wheels and your system for the harsh conditions of the lunar surface, that loose regolith, and you lay down a road, how do your wheels go over that road? It looks like the Monash Nova Rover team have opted for a hot pink 3D printed sheet of pavers on some fabric, which is a lightweight and novel solution of how do you combine a sheet of pavers to cover a large surface area to fit within the weight constraints of this task. So the total mass for the other tasks is 50 kilos, and for this one, it's about 60. And it raises even more questions of how much does your rover and your systems weigh in order to be sent to the moon? Which systems are critical? How can you really optimize? With that, I think they may have just done it for the construction task. And if they move on to the next and nearest activity available to them, which is the excavation and deposition task, up on the screen you can see that square-ish pile of soil. It is their job to excavate from that pile, and deposit in the metal hopper, which is coming out of the processing plant just to the bottom left of the screen with that control panel. And this is the exact task that the Australian Trailblazer lunar rover will have to complete as part of its remit to the NASA Moon to Mars initiative, where then Australian rover, a foundation services rover, will be required to excavate regolith from a regolith acquisition zone, a RAS, and then deposit it in a metal hopper into a NASA payload, which will attempt to extract oxygen from that regolith on the lunar surface, demonstrating for the first time the in situ resource utilization, the ISRU, of valuable resources like oxygen from the lunar regolith. And as we continue to go onwards to the moon and further to Mars, technology like this will be required to be tested and validated under extreme conditions, like on the surface of the moon, to make sure that there is enough breathing oxygen, which you can combine with hydrogen to use for things like watering agriculture to create food, using as potable drinking water, and even as propellant for rockets, some rocket fuel. The extraction of oxygen, together with metals from the lunar regolith and other volatiles like hydrogen, is the focus of many researchers from around the world, including my host institution, Swinburne University. Shout out to the Lunatics Research Group. And with about 25 minutes left on the clock for a task time finish of 11:25, the Monash Nova Rover team from Melbourne, the current podium sitters at place number 1, have 2 activities left. Tuning in, wondering why the rover is hot pink, it's because their task is to raise awareness of female engagement in STEM. As we go onwards to the moon and further to Mars, we need everyone, every passionate and driven individual, to work together on complex systems like rovers. And just on the screen, you can see that pivot steering coming into play, each individual wheel rotating on its axis, trying to interpret the rover commands sent to them by the base station operators. And this control, I will remind you, is entirely designed and built by undergraduate students, also juggling part-time work and full-time study. in their spare time, and I can tell you firsthand, no one at university tells you how to build a rover. They all do it by themselves. Each year, year on year, learning from their mistakes. And for those who weren't present at the trophy building ceremony, the winning teams, the first, second and third place of the Australian Rover Challenge, get to take home a lovely trophy which is made from all the failed 3D printed parts, blown electronics and essentially anything that didn't work or failed as part of the rover development, which they hot glued and spray painted gold together, symbolizing that the winning teams got there from the combined failures and learnt mistakes of all the teams, trying to symbolize that we as an Australian community are going to get there together. We're going to learn from each other and continue to improve each year, year on year, as the Australian Rover Challenge continues to grow. In the first installment back in 2021, right after COVID, we only had 3 Australian teams. Then we had 5, now we have 7, with several other teams currently not participating this year, but slated to compete next year as we scale up to more Australian teams from every state across Australia and even the world, with a quick shout out to the Polish team coming all the way from Poland on a very early flight. As our first international competitors, they are currently ranked number 3. Let's see if they can take the title, take the throne off of Monash Nova Rover when they're competing later today. And it looks like the rover's going back for a second pass over the pavers it's laid down. And to score points for this task, each individual paver you see there must make complete and full contact with the ground and remain within the boundaries of that spray-painted blue line together with rope. This raises many interesting questions like, how many pavers do we put down on the ground? How big are those pavers? How thick are they? What material are they? How do we interconnect them? How do we deploy them? And it looks like they've gone over a second pass with about 21 minutes left on the clock, with 2 other activities scattered across the lunar surface, the simulated lunar surface out here today. And it looks like the rover is approaching the RAS, the regolith acquisition zone, with its large bucket scoop driven by 2 linear actuators on the front of the rover. This allows that scoop to descend down like it is right now. It changes its attack angle, which is the angle of the rake, the cutting edge of that scoop, as it tries to dig up regolith from that RAS and then deposit it in the hopper, just coming up on the screen, on the right side of the screen right now. And that hopper and this entire activity represents exactly what the Australian Trailblazer Foundation Services rover is going to have to do as part of its remit to the NASA Moon to Mars initiative, which seeks to send an Australian rover designed and built right here in Australia to the lunar surface. And it is my hope that this will inspire the next generation of Australians to pursue space studies or space enthusiasts, as we need everyone from every discipline to not only build the infrastructure down here on Earth, but to make sure that the operation of the rover and those systems out there in space remain working, remain functional, and don't turn into space debris. And for those who aren't aware, space debris is a huge issue currently being tackled by many companies around the world, as well as several space agencies, which is every time you launch something into space, you create debris. And that debris over time And with a perfect mouthful of dirt, the rover is going to take its first bite out of the RAS. Now, for those who aren't aware, the interesting thing, and this is the focus of my PhD work, which is the mechanical behavior of this regolith, of this extraterrestrial soil, behaves quite differently to the material we have here on Earth compared to the material we have on the Moon. And that is because the material here today is a loose sand. However, the material on the lunar surface is comprised of crushed, pulverized rock from billions of years of impacts from micrometeorites and solar radiation, creating extremely jagged pieces of essentially glass and rock, lithic fragments with particle sizes ranging down to submicron, which means that the rock dust that levitates off the surface can be finer than the particles that create smoke. That's right. Little pieces of rock, smaller than smoke particles, getting everywhere. And when you dig into lunar regolith, some of the unique properties is because it's so jagged and composed of such small pieces, you can create trenches with nearly vertical walls. What does that mean, Daniel? Well, if you've ever been to a beach and you've tried to dig a hole into the ground and the walls start collapsing, that shows just how different the mechanical behavior of this soil is. On the Moon, the Apollo astronauts dug about a 30-centimeter deep trench with nearly vertical walls, which raises many interesting questions such as how do you dig and how do you build infrastructure on the lunar surface where the material behaves so differently? As the Nova Rover team, it takes its first bite out of the RAS, and with each bite from that RAS pit pile of sand, we will weigh the amount of soil in that hopper, and this rover teams are scored based on the total amount of regolith deposited in that hopper at the end of the task. This team with the most amount of soil at the end of the whole competition wins the total amount of points, and each team is scored based on a percentage of that top team, which is a novel way to get teams to really think about how much dirt do we need to get? Should we spend more time on other activities? Let's see how they play it out, as a huge amount of game theory comes into it now. Adding some of the unique things that need to be considered when you're excavating on the Moon, the tow bar force, or the force required to excavate into the soil. And with its second bite, a huge mouthful of dirt right there. You can see at the rear end of the wheels that loose pile of soil building up on those wheels. On the lunar surface, because the gravity is 1/6 that of the Earth, the amount of force or the traction that you can generate from the rover wheels is significantly less, which means the force required to dig into the soil still remains high, but the amount of force of your acting on your rover is quite low because there's less mass, because there's less gravity, and the traction is quite difficult on the very loose regolith, which means there is a real risk that as you dig into the soil, you will flip your rover because there is not enough force acting on the wheels to keep it down, cemented on the ground. And this requires many novel solutions in terms of how do you actually excavate soil? Do you use a bucket scoop like the lunar rover here? Do you use a drill? Do you use a cylindrical barrel with little teeth on it, like the NASA RASOR, the RASSOR, which is a novel little rover designed and built by NASA? And if you Google that, you can see some amazing videos of how NASA has attempted to approach this issue of excavating regolith on the lunar surface. It is essentially a four-wheeled rover with two large barrels on either side of it, actuated by linear actuators. And as the barrels rotate, they counter-rotate, meaning they run in opposite directions so that any force acting on the rover is equaled out, enabling the rover to dig quite deep and quite efficiently into the ground, but also use those barrel excavators as secondary wheels in case it gets stuck. So if their wheels do get stuck, they can almost sort of grab onto the nearby material and try and move themselves. So a really novel solution to a really tricky problem. And it looks like the rover is holding up its dirt like Lion King, waiting to deposit it into the hopper. They've got about 14 minutes left on the clock with an end to the task time at 11:25. One of the ways we're scoring this task is simply by the amount, the total mass of soil that each team has deposited into that hopper. However, if you're designing a rover for the moon, for mining applications in terms of using the resources available to you on the surface, use common things like kilograms per hour, how efficient or how much material can your rover dig up in time, but also how much energy does it take to dig up that material. You can dig up, 100 kilos of regolith, but if you're spending a lot of energy to do so, your process is not efficient. And efficiency is everything. And for those tuning into the live stream and spectators out here on the pitch, I'll just remind you of the Make History speaker series down here in University of Adelaide. We have a free public lecture available to everyone, Writing History in the Stars, with the MC John Coulton, who will be joined by Dr. Kimberly Clayfield from CSIRO, Dr. Sarah Cannard from Nova Systems, and Dr. Matthew Tetlaw from Innovore to discuss how space science is addressing humanity's greatest challenges using satellite imagery. And we can do that by using satellites to image hazardous events like floods and fires. And just quickly, here's Nova Rover's second bite. A huge amount of regolith in that hopper. Let's see how many bites they want to take from this RAS. And just on that Making History speaker series, it will be hosted at 5:30 tonight in the Braggs Lecture Theatre, doors opening at 5. It is a free event. You can register online. For more information, please find any of the judge or officials here today. And for the rover participants, may I remind you that the Animals Anonymous are here today from 10 till 1, where you can interact with some native Australian wildlife, including baby crocodiles, snakes, birds, and last but not least, a cute little quokka named Queenie. And you can see the rover doing a reverse park right here, just over a rock. Same issues happen on the moon as on Earth. How are your rear view cameras? And it looks like that back wheel and traction on the surface, just highlighting the extreme terrain on the lunar surface, which may pose risks to rovers operating. And they eat it for breakfast. With 10 minutes left on the clock today here at the excavation and construction task as part of the third installment of the Australian Rover Challenge, the Monash Nova Rover team right here hailing from Melbourne have already completed activity number 4, the construction activity worth 35 points, which is that sheet of 3D printed hot pink pavers you can see out on the field. They are currently attempting activity number 3, which is excavation and deposition, worth a total of 40 points, with the winning team depositing the most amount of material, gaining all 40 points, and all the other teams getting a percentage of that based on the amount that they deposit. And with just under 10 minutes left, they have yet to complete activity number 2, which is debris clearing, worth a total of 20 points, which consists of debris out there on the field in the valley, which the rover needs to clear out of that zone. And they've already achieved 5 points for descending down the ramp, down the lander, and Monash Nova Rover's approach for the third time with a mouthful of regolith to deposit into that hopper. And let's get a huge round of applause. This is no simple feat. What you witnessed today is the combined efforts of nearly 100 undergraduate students from Monash University working diligently, sometimes extremely late hours, sometimes even no hours of sleep on their rover, named Waratah, I believe. Yes? Yes. Looks like this rover is quite hungry. It's going back for a fourth approach. With the task time finishing at 11:25, let's see if they'll have time to clear the debris that still remains out there on the pitch, worth a total of 20 points. Looks like they're really gunning for that total 40-point maximum for this activity. And this just highlights some of the strategy that comes into not only designing and building a rover, getting it to do all the activities in each task, but also considering which tasks do we do and in what order? How much time do we spend on each task? Which tasks can we complete? How do we get those points? And this is something that I used to think about back when I was part of a rover team. And its fourth bite looks successful. And a phenomenal effort with the fourth bite from the Monash Nova Rover team from Melbourne, with just over 5 minutes left on the clock, with the total finishing task time of 11:25. Let's see what they do next. Will they get some more regolith, or will they attempt the debris clearing task? What is worth more points? And a quick shout out as well. Congratulations to all those teams selected to participate at this year's University Rover Challenge over in the US. The University Rover Challenge is organized and hosted out at the NASA Mars Desert Research Station in Utah as part of a simulated mission to Mars. And this is a competition I used to compete back in the day. And I can attest that it is difficult, exciting, and a fantastic opportunity for students from around the world to compete under extreme, harsh conditions, working with their base station out the back of a U-Haul trailer. I remember very vividly not being able to stand up as I'm trying to operate the rover out there in the hot Utah desert heat. And for those interested, this is one of several rover challenges from around the world. We are rapidly growing here in Australia and are happy to host our first international competitors all the way from Poland. Yeah, woo! As we continue to grow each year, it is our vision to get more Australians into the development and design of rovers for this challenge. And there it goes with its fourth bite. really getting a lot of regolith into that hopper. And with 4 minutes left, what will they do next? More regolith or debris clearing? And it seems like this is a game of hungry, hungry hippos as it goes back for its 5th bite of regolith. Will they attempt the debris clearing task? Time will tell with just about 3 minutes left on the clock. Will they be able to dig up this next pit? As the deeper you go into the sand, the harder it gets to excavate. And this is just highlighting some of the real world scenarios that will happen to a rover on the lunar surface. As you can see those piles of sand and the little ditches being dug by the wheels. The lunar surface, of course, is covered by a loose layer of crushed rock called regolith, which is extremely porous, which means very loose at the near surface, but becomes extraordinarily dense with depth. So the density with depth relationship is such that the famous boot print of Neil Armstrong as he took his first steps on the lunar surface have near perfect resolution. You can see the exact imprint of his boots. And there's a 5th bite from Nova Rover with 2 minutes left on the clock. What will they do next? So up next, we have the University of Queensland Rover team starting at 11:30 up on the field with just under 2 minutes left for Nova Rover. They're going back for a 6th bite, would you believe? Really trying to maximize the points for this activity. 40 points up for grabs. How will this pan out as the other teams compete? Of course, the total 40 points is awarded to the team with the most amount of regolith deposited into that bin, with other teams scaled for the amount of regolith they deposit compared to the number 1 team, with 20 points left for debris clearing, which I don't think they'll make in time. They may have or may be able to achieve a total of 80 points up for grabs if they score maximum 35 points for that construction task for the pavers out there on the pitch. With 1 minute left, can they get this last bite in time? A nail-biting finish out here on the Australian Rover Challenge. Waving to the audience. Let's get a huge round of applause for Monash Nova Rover, hailing all the way from Melbourne. What a fantastic performance as our second competitors for the excavation and construction task. And coming up next at 11:30 is the University of Queensland, the UQ Rover team.
Australia is a nation of creators, aviators, protectors and innovators. From aviation's first light to the dawn of the jet age and beyond, at Boeing, we're building the future together here in Australia. Inspiring those in pursuit of new frontiers, connecting, protecting and exploring our region and the world. Home to the broadest aerospace portfolio in Australian industry, powered by talented, dedicated and diverse teammates. Delivering manufacturing excellence, building composite aircraft parts for the world's most efficient airplanes, using advanced robotics, materials and digital technologies. Never compromising on safety or quality, always focused on sustainability. Solving tomorrow's problems today with Australia's leading researchers, scientists and universities, developing new military platforms and communications networks, and helping ensure they are always mission ready. Keeping customers airborne by providing the services they require. We stand shoulder to shoulder with Australians during natural disasters, on the front line and in peacetime. We support veterans and our community, and we nurture the next generation of aviators to excite, to be bold. Boeing Australia. Made in Australia by Australians for the world.
Welcome back to the third instalment of the Australian Rover Challenge. Right now we've got the University of Queensland UQ Rover team setting up for the excavation and construction task. Their start time, or their allocated start time, 11:30 to 12:10, a total of 40 minutes, with 100 points up for grabs. Up on the screen right now you can see UQ Space coming from Brisbane, Australia, with a total score of 81.7, comprising 77.2 points from their CDR and SAR submissions, the Critical Design Review and System Acceptance Review. And these are the formal documents that all teams must submit to us, the judges, to review their development cycle is keeping in pace with where we expect the rovers to be, to make sure that they're assembled and ready for the challenge in time, as well as acting as the main thing that we use to validate if the rovers are ready to come and compete. As we expand, more teams will come, and we won't be able to field every team, so it will be a down select. And this happens much like the University Rover Challenge, who just down selected to 36 teams from just over 100 teams. And these documents, the CDR and SAR, are common documents that all officials working at NASA and space agencies and industries around the world have to complete as part of their systems engineering and project management. So if you're ever going to send something to space, you have many documents to write up. And of course, 4.5 points as part of the Australian Space Agency post-landing task, which we hosted yesterday on this very same pitch, with 100 points up for grabs for that. And it looks like the rover is taking its first steps. There it goes, in an attempt to descend down the ramp for an initial 5 points as part of Activity 1. All 6 wheels have to make complete contact with the ground. And for those watching online and those spectating here today out on the pitch, this is not as simply as driving an RC car. You don't just turn it on and press go and hope that it goes. This is complex. This is a fully integrated and complex system comprising sometimes years of work from undergraduate students who are working full-time, studying full-time, working part-time, hopefully, and then volunteering with all their extra time on the side, building these rovers. And there it goes, with pace, down the ramp. There's 5 points. Let's get a huge round of applause, everyone. Interested in getting involved, if you're in primary or secondary school, or you have children in school, there are things like the FRC robotics competition, where you can form student teams to build rovers much like this and compete at a huge competition with over 100 teams comprising students from around Australia, competing in a challenge not too dissimilar from this, but not on the lunar surface. Your task is to design rovers to score points as part of an intense battle royale, but it's not fighting each other. You're fighting against the clock to score points of shooting cones, placing balls, and moving. As well as, might I recommend checking out organizations much like One Giant Leap. If you want to go to space camp, One Giant Leap can take you there. One Giant Leap Australia operates here in Australia and has a base over in the US. So if you want to go visit NASA as a space camp cadet, check it out online. And again, just highlighting how difficult it is to not only get your rover moving and functional through the communication, the wireless communication happening over radio at 2.4 and 5 gigahertz. So rovers cannot use Wi-Fi because there's no Wi-Fi on the moon, neither is 5G or GPS. Not yet anyway. Nokia is actually planning to send a 5G module to deploy 5G on the lunar surface later this year as part of their rover with another private company. And this will try to demonstrate that telecommunications out in space is tricky. You can't use simple things that we would get on our phone. But out here today on the pitch, most teams use 2.4 and 5 gigahertz communications to ferry instructions from their base station team to their rover. And then the more complex thing is, how does your rover execute those instructions? How is the design of the mechanical, electrical, and software systems of your rover, including its subsystems like the wheels, drivetrain, chassis, robotic arm, and other subsystems like the paver deployment system you can see on the back of that rover, almost like a cape hanging off the back. And the lunar surface will actually be more difficult to traverse than the pitch you see here today, and that is because the surface of the moon is covered by a loose soil called extraterrestrial regolith, which is ultra-fine, jagged pieces of glass and rock that acts like flour almost. With any load pressed into it, you can easily deform and create almost perfect boot imprints like those of Neil Armstrong and all the amazing Apollo astronauts that visited the moon back in the late 60s and early 70s. But with depth, that means the deeper you go into the surface, the material becomes extraordinarily dense. So dense, in fact, that if you've ever seen a construction site or the building of a road, the big compactors, those huge giant rolling machines that try and compact down the soil, that is looser than the material we find on Earth, which means that the compacted soil at shallow depths, just about deeper than 30 to 50 centimeters, deeper than that, it gets so hard it acts almost like concrete. And then that raises questions of, how do you operate in an environment like that? How do you dig? How do you build infrastructure? If you want to build a building, where do you put your foundations? With 10 minutes into their allocated 40-minute time window, with a finish time at 12:10 and a start time at 11:30, UQ Space are attempting to complete 3 activities as part of the excavation and construction task here today, the Australian Rover Challenge, worth a total of 100 available points. The rovers are expected to descend down the ramp for 5 points, which the UQ team has successfully completed. Then they have 3 different things to complete. The debris clearing, which you can see is those loose pieces of debris within the valley on the side of the rover pitch, worth a total of 20 points. The excavation and deposition of regolith, much like Nova Rover did in the previous task, the rover must, or can, excavate regolith from the surface and then deposit it into the metal hopper out there next to the processing plant, worth a total of 40 points. And last but not least, the construction of a road out there on the surface using the pavers that the teams have designed and built themselves, including but not limited to interconnected pavers rolled out by the rovers, which the rovers must then drive across to demonstrate that they have successfully constructed a road out on the surface to help with the issue of dust mitigation. So as you drive across the surface, you kick up dust, and that dust poses some serious hazards. The more journeys that you take on the surface, the more dust you kick up, and the longer you're there, the more vulnerable your systems become to wear, the slow but inevitable wear and abrasion that happens on your wheels, in between the joints of your motors, at all seams, at all entry points of your rover. Dust will get there. And it's not as simple as sending a mechanic to the moon. You have to design for it to make sure that your rover or mechanical system can survive the harsh lunar environment for as long as possible. And you can see those rover wheels as part of the 6-wheel Rockaboga system of the UQ Space team, highlighting the difficulties associated with traversing across the lunar surface. The loose material can be easily moved aside as the rover wheels try and gain traction into that loose material, and this is a function of several different things. How big are your wheels? How wide are they? And that tells you the footprint of your rover on the ground. How big and what are the geometry of the grousers across the wheels, and those are the fins you can see on the 3D printed wheels of the UQ team. And you can see right there the sand getting caked in between the grousers with no traction. This highlights issues of how do your rovers actually how do your wheels bite into the surface to make sure that they can move. And with loose sand, loose material comprising the surface, this is no easy, simple task. And on the moon, it gets harder because the regolith gets softer, gets more tricky to dig into, but also it's 1/6 the gravity. So this can both go in your favor, reducing the down force or the total mass of your rover pressing onto your wheels into the surface, but also, as Nova Rover demonstrated, if you've got less mass of your rover, you've got less traction and sort of a drawbar pull force, meaning that as you're digging into material, you're acting on a force trying to dig in. So if you've got a shovel and put it into sand, if it's compacted sand, you need a lot of force. If it's loose sand, you can just slide the shovel in and dig a hole. On the moon, this means that if you're trying to dig into something and you put too much force, you're at serious risk of damaging your rover or even flipping it. A quick reminder for those on the live stream and those here today watching at the simulated lunar surface of the 3rd Australian Rover Challenge. We are hosting a free and public event. As part of the Make History speaker series, we have Writing History in the Stars, a seminar delivered by John Coulton together with Dr. Kimberly Clayfield from CSIRO, Dr. Sarah Cannard from Nova Systems and Dr. Matthew Tetlaw from Innovor, to discuss how space science is addressing humanity's greatest challenges using satellite imagery. So this is going to address things like how can we use satellites to track bushfires and floods, to track weather, hurricanes approaching cities and towns on the coast and inland. How can we use satellite imagery to optimize the efficiency of agriculture to track crop harvesting, such as when and where do we harvest? When and where do we spray pesticides? You don't need to spray an entire field. Maybe you can just spot localized areas. As well as also CSIRO's recent Aqua Watch program, which aims to measure the water quality of some streams and rivers to develop, much like how we have a weather forecast for the water quality, and that is the Aqua Watch program at CSIRO. And for the students available here today, we also have from 10 till 1 the Animals Anonymous wildlife program, where students will be able to interact with native animals from Australia's ecosystem, including a little quokka named Queenie, and it looks like the UQ team are calling it intervention. And this is where the base station team opt for an intervention where the field team can go and perform basic maintenance on the rover. This intervention carries with it a 10% penalty to all available points to the team. So it's the risk and evaluation. You need to make a call, a judgment call with your team, sorry. Do we go fix it and take the penalty, or do we continue to try? And it looks like the UQ team are taking that haircut to try and optimize how they can complete the rest of this task. And during this time, the base station team are communicating with the field team via walkie-talkie. Although you can do this here today at the Australian Rover Challenge, when things go wrong on the moon, you can't send a technician to go fix it. So again, this is trying to get students to think about how do we design a robust enough system where interventions are required, and this is extremely complex, not only for students, undergrad students here today, but also professionals, as I can attest to, working on a rover over at NASA Ames, one of the wheels that was designed by JPL, when I helped mount it onto the chassis of the rover at Ames, it hit itself. The wheel clearance to the chassis wasn't measured in great enough detail, and it just highlights how we had the same issues in the student team when I was on the rover team, and everyone makes mistakes, from undergraduate students all the way to professional engineers at NASA. And that just comes to show how we're all learning, we're all making mistakes and trying to optimize and figure out how to explore the lunar surface and deep space safely, robustly, and sustainably. So right now, the UQ rover team has 20 minutes left on the clock with the finish time at 12:10, with a total of 40 points starting at 11:30 for the excavation and construction task. Watching on the live stream, you can see right there, working on the wooden trestle tables, the base station team. So this is the contingent of UQ Space who are controlling the rover, and that base station tent is just out the back behind the bleachers. And this is a little area that represents the HQ, the mission control that would exist on the surface of the Earth, controlling the rover remotely. Not live, of course, because the moon is quite far away and there would be a delay on the order of a few minutes. And the base stations that we provide here today are quite luxurious and spacious compared to the little U-Haul trailers that we had to work with over the University Rover Challenge in the Mars Desert Research Station. And the base station team, their job is to receive all the input coming live from the rover, including rover video camera streams and input data on the positioning and power of the motors, as well as the other subsystems on the rover, such as the paver deployment mechanism, which you can see like a cape draped across the back of the rover. Those look like black acrylic sheets with interconnections. And that is for the construction activity, worth 35 points for this task, out of a total of 100 points as part of the excavation and construction task for the Australian Rover Challenge, with 500 total points up for grabs. This task is comprised of 4 main activities. Number 1, descend down the ramp, which the UQ team have successfully achieved for 5 points, and which the other 3 activities which they can complete in any order include the debris clearing, which is some debris located over on the right side of the pitch, worth a total of 20 points. The excavation and deposition task, worth 40 points, which is the excavation of the regolith out on the left side of the field and deposition into a hopper connected to the post-processing plant in the bottom left of the field. And this is the exact task that Australians will have to complete as part of the Australian Trailblazer lunar rover mission, as part of our cooperation and ongoing collaboration with NASA's Moon to Mars initiative. And last but not least, the construction task, where those pavers will be deployed by the rover in a designated area, and they'll be awarded points for each paver successfully placed on the surface for a total of 35 points. And with that, the human technicians are off the field and the rover is back into play at the end of the intervention with a 10% haircut to this task. Let's see if the rover can progress its way onwards to the other three activities as part of the excavation and construction task, worth a total of 100 points as part of the Australian Rover Challenge, with 8 teams across Australia, including a team all the way from Poland, our first international competitors. And up on the screen right now, you can see the University of Queensland UQ Space Rover team trying to make its way through the surface, highlighting just how difficult it is to traverse this loose, sandy material. And you can see across the back of it, draped like a cape, the paver system that is required to be deployed in a designated area as part of the construction task. But also mounted on it is the excavation system that the UQ Space team will use to try and excavate regolith from that regolith acquisition zone on the left side of the field. And you can see up on screen right now the boundary blue outline of the construction area that the rovers must cover to be awarded points. A total of 35 points available. They get points for each paver successfully placed on that surface. "13 minutes left on the clock with the end time of this task for the UQ Space team at 12:10. Coming up next is the University of Melbourne rover team from Melbourne, Victoria, down here in Australia. And you can see currently the base station team trying to navigate that surface and get the rover moving. And just a reminder, the base station team is located right here at the Challenge Arena at the back of the bleachers, where the only input they're getting is the video feed and the input data from the rover transmitted wirelessly via radio, often at 2.4 and 5 gigahertz, from the rover's antenna back to their base station antenna. And the field team's job is to make sure that nothing goes wrong, and the base station job is to try and make sure the rover gets operated. And the only one time that they can communicate is during an intervention called by the base station team, or complete e-stop called by the field team, sorry. And the e-stop is the emergency stop you can see on the side of the rover there, the big red button. And that cuts all power to the rover in case of emergency and also ceases the task immediately. And with just about 11 minutes left, let's see if the UQ Space team can pull themselves through. And right now, up on the live stream, you can see the current view, exactly what the rover operators see with the command prompt. It's how they control the rover with two video feeds showing the front two rover wheels and the back rover wheel together with its paver deployment system. And this is just highlighting how difficult it is to figure out where and what your rover is doing on the lunar surface, because the only input you have is through those video feeds and whatever data that you can transmit across those radio, which have a limited bandwidth. And of course, on the lunar surface, you would have a 4-minute delay. And I've just heard they've called for another intervention. Once again, up on the screen, the exact view that the rover operators have of their rover, the UQ Space team, with 9 minutes left on the clock with a finish time at 12:10. As part of the Australian Rover Challenge excavation and construction task number 2 out of 4 tasks. Yesterday we had the Australian Space Agency post-landing task. Today, of course, is the excavation and construction task. Tomorrow we have the iSpace Space Resources task, where the rovers will have to go and excavate icy regolith, which just means frozen soil, to extract water to demonstrate that we can get liquid water from deposits on the lunar surface to try and keep humans alive in space for longer. And last but not least, task number 4, the mapping and autonomous task on Sunday, sponsored by our premier sponsor, Boeing. The Boeing mapping and autonomous task challenges students to autonomously or semi-autonomously map the surface of this arena to tell us, the judges, where the pieces of infrastructure is, and whilst doing so, navigate the extremely difficult terrain as well as the obstacles, including the very real but fake rocks that we've put out on the surface and the undulating terrain. And you can see up on the screen now the piles of loose regolith that surround the rover wheels, and this material out here today on the simulated lunar surface is representative but not quite exactly what you would find on the lunar surface, because on the moon there is no atmosphere, which means there's no wind and there's no rain. So the only thing acting to weather the soil out there are micrometeorites and cosmic radiation coming from interstellar stars and our very own sun blasting the surface of the moon for billions of years, creating an extremely hostile place where the soil, which we call extraterrestrial regolith, is extremely loose, extremely jagged, and poses serious risks to the traversal of rovers as they drive across the surface, but also the safety of human astronauts. As the Apollo astronauts can definitely attest to, the dust that gets kicked up as they operate on the lunar surface gets into and on absolutely everything. Onto their visors, completely scratching it up so that they couldn't even see out of them, but also bringing it back into the lander as it's stuck onto their clothes, meaning that as they were resting up for the night inside the lander, they were inhaling these tiny jagged pieces of glass, essentially getting asbestosis, but only this time it's silicosis because the particles of jagged rock are made of silicates as they are rock. With just over 5 minutes left on the clock, with a task finish time at 12:10, the UQ Space team is trying to maneuver through that lunar regolith out on the field. And coming up next at 12:15, the University of Melbourne rover team, the URT, with their attempt at the excavation and construction task. And after the UniMelb rover team, we will have a break for lunchtime with the the next team coming up being the University of Technology Sydney, UTS, at 2 p.m. The Project Scorpio team hailing all the way from Poland, starting at 3:30 p.m. And last but not least, the host institution, University of Adelaide, their rover team starting at 4:15. with that, at 12:10, that concludes the end of the UQ Space excavation and construction task. Let's get a huge round of applause for the competitors today. And let's see what they can pull through with the remaining Saturday and Sunday tasks, the space resources task on Saturday, and the Boeing mapping and autonomous task on Sunday. Up next at 12:15, starting the University of Melbourne Rover team, the URT. And it is their job to score as many points as possible out of the 100 available points for this task, which includes 5 points for descending down the ramp, 20 points for clearing the debris on the surface, 35 points for constructing their dust mitigation road, as well as 40 points for the excavation and deposition of regolith from that RAS. You can see just to the left of the screen right now, which is the pile of regolith that an Australian lunar rover, as part of the Trailblazer mission, will have to excavate from and deposit into a hopper as part of the NASA Moon to Mars program, where an Australian rover will, in the not so distant future, maybe even a few years, depending how the development goes, deploy a Foundation Services rover on the surface of the moon, where it will, much like today's challenge, excavate from a RAS, a regolith acquisition zone, deposit into a hopper on a NASA payload, and the NASA payload will then attempt to extract oxygen from that regolith, which just means it will heat up to extraordinarily high temperatures, where the volatiles, including hydrogen and oxygen, will be released from the regolith. And if you keep going with increasing temperatures, you can actually extract metals from the soil. And this is just a demonstration of some of the novel techniques that is being pioneered by the space industry with application to down here on Earth. Not only do you have to use the materials you find in space, you have to do so sustainably and efficiently, which has huge knock-on effects to the technologies we use down here on Earth with our resources. And one common topic of conversation is the efficient use of energy out there in space. And currently up on the screen, you can see the University of Melbourne Rover team, their current score at 141.4 points, putting them in second place. Hailing from Melbourne, Australia, they achieved a 66.4% out of a total 100 points for their critical design review and system acceptance review, the CDR and SAR, which are formal documents the teams have to submit to us, the judges. And this outlines how ready their rover is to compete at the challenge, but also highlights the documents that if they decide to work out in the space industry, they will have to complete these documents in the development of their rover or payload or instrument, making the participants of this challenge have real-world applicable experience. And of course, they got 75 points out of a total 100 points at yesterday's Australian Space Agency post-landing task, putting them in a very solid position to try and take the throne from the current number one Monash Nova Rover team. And you can see up on the screen the lander just to the left that the rover has to descend down. In the middle of the screen, where the smiley face is the construction area where the teams have to deploy their pavers there for their road. And just in the top right of the screen, the post-processing plant with that control panel and a little ramp down to a hopper where the rovers must deposit that regolith. And they get points awarded based on the total mass of regolith that they put into that hopper, with the winning team, the best team performing, scoring the total of 40 points, with each team scoring points based on how much mass of soil that they deposit relative to that number one team. So that introduces lots of tricky strategy considerations, such as which activity do we do first, how long do we spend on each activity, to try and maximize points. And this is an excellent demonstration of the critical problem-solving skills that students in the Rover Challenge have to consider, not only during the design and development of their rover, up on the screen right now. Welcome back. For those who on the live stream or the spectators currently down here on the pitch, on the screen you can see the University of Melbourne Rover team, the URT, with their red and blue rover, trying to troubleshoot as part of the excavation and construction task. Their time slot for this task was 12:15, with 40 minutes. That puts them at an end time at 12:55. Let's see if they can get things ready and moving in time for the attempt of those different activities. You can see up on the screen a total of 100 points, 5 points available for descending down the ramp, 20 points for clearing the debris on the surface, so moving those pieces of debris out of the allocated area, 40 points for the excavation and deposition of regolith from the RAS, that regolith acquisition zone you can see as a pile of dirt out in the field. Its deposition into a hopper where the total mass of soil deposited at the end of the task will give them a scaling variance of how many points they get of those 40 available. And last but not least, the construction. For 35 points, the construction of a road on the surface. Many teams have 3D printed or mechanically connected different pavers, individual tiles, to try and cover that area, that 1.2 by 2 meter construction area. And this is all these activities are trying to showcase the real world challenges that rovers will have to complete on the lunar surface. They're going to have to clear debris to make a road. They're going to have to try and cover that road with a piece of material that will prevent the dust from being kicked up as the rover's driving around, because as you drive onto the surface, the more you drive and the longer you drive for, you're just kicking up more and more dust that stays suspended above the surface, not by air, but by electrostatic forces. And this has been observed on the lunar surface as regolith floating as high as 10 meters above the ground, levitated, causing some sensational views by the Apollo astronauts as the sun rose above the horizon. You can see an amazing sunset caused as the light filters through and is obscured by some of those particles of dust. And you can see up on the screen now some troubleshooting as the robotic arm maneuvers up and down, consisting of what looks like a plastic shovel zip tied to the end of the arm. It's a great saying, if it's stupid but it works, it's not stupid. And of course, if it works out here on the Rover Challenge, that's all that things matter. Duct tape, zip ties, hot glue, novel solutions to practical challenges. And I can attest firsthand the amount of things we had to zip tie to our rover as we were competing in the University Rover Challenge. The rover was being held together by zip ties and a dream. And at 12:22, with a start time of 12:15, 33 minutes left on the clock, the University Rover team from UniMelb are deploying their rover up on top of the lander to score points for that first activity. 5 points up for grabs for descending down the ramp, getting all 6 wheels in contact with the lunar surface. And for the observatory spectators out there, you'll notice the red and blue color scheme for the rover is reminiscent of a favorite childhood cartoon. Its first steps down the ramp onto the lunar surface, blazing a trail as it pivots left. And for those interested, the pavers for the construction task can be in one of 2 starting locations. The payload bay at the rear of the lander, just to the right of the screen here, or on the rover as it starts. Looks like the University of Melbourne Rover team is reverse parking to try and pick up those pavers that they've deployed in the payload box. If you've ever tried to reverse park with a car, try doing it with a rover through a little laptop screen. And it is their job to cover that designated construction area with the pavers that they've made. And these pavers have no specific weight or dimension constraints because we wanted to let the teams have complete design freedom. As this is a novel engineering challenge, we just said cover that area with pavers and make sure it's within the total mass limit for this task. So the rover and the pavers, the total system weight can be no more than 60 kilos, with the other tasks having a total of 50 kilos, with a combined weight of everything the rovers bring being 80 kilos, and the total dimensions of their rover being 1.6 meters in every dimension. We're trying to get the teams to think about how do they optimize dimension and mass constraints, as if you're designing a system to go to the moon or even space, you will always have size and mass constraints, because mass is money and money is time. Let's see if they can pick up their pavers with their novel and interesting, bold maneuver to try and pick up the pavers with what looks like a big bolt threaded through a plastic shovel, zip-tied onto the end of their robotic arm. Let's see if it plays out for them. And if you've ever tried to thread a piece of string through a needle, try threading a bolt through a triangle paver box. And on heads-up display right now in the live stream, you can see the base station operators situated at the back of the bleachers right here at the issue. Make sure nothing goes wrong out on the pitch. And it looks like they've managed to grab hold of that first paver stack. And like a house of cards, let's see if they can pull it into arrangement. And the solution that the Unimel rover team has looked like to approach this construction task is laser cut wooden panels threaded together with string, a lightweight and novel solution to try and cover that lunar surface with pavers to try and reduce the impact of dust that gets kicked up by the rovers as it drives across the surface. And it is the rover's job to not only grab these pavers, but put them into position in a very tight 1.2 by 2 meter allocated area, but also make sure each of those pavers are in complete contact with the ground and within the boundary that we've provided them. Of course, rover teams are awarded points for minimizing the mass of their solution, with the team with the most lightweight solution of all those pavers being awarded up to 5 points. And it looks like it's going to drag this blanket of sheets across the lunar surface to try and pull it into a position. This is no easy task, as the rover has to do this reversing while navigating obstacles including the lander, hills, tight spaces, rocks, to try and get it into a position at that front area of the rover pitch. With about 25 minutes left on the clock, a task finish time of 12:55. The team is currently sitting on a nice 5 points for descending down the ramp, with 95 points up for grabs for clearing the debris, excavating, depositing regolith, and of course constructing that road with the pavers currently in the robotic arm. You can see up at the screen right now that sharp boundary from sand to grass, and the rover is really trying to be careful with how it maneuvers right now, as if any wheel or point of the rover, of any point of the wheel, sorry, of the rovers make contact with that grass, that is out of bounds and an immediate disqualification of the task. So they're really trying to thread a needle right here as they're dragging their pavers through a narrow corridor. And this is a true test of how well and how practiced are your rover operators, and how much testing and field testing have you done with your system prior to the competition, as everything is not done until it is tested. The rover is waving to the audience right now. With this narrow corridor that the rover is trying to drag these pavers across, you can see just how complex it is operating a rocker bogie system with 6 wheels. The rovers have fixed dimension and mass constraints, and the operation of these rovers on the lunar surface is extremely difficult, as all the teams have experienced firsthand. You can get bogged down, you can get flipped. Sometimes things go wrong, and this challenge is all about testing students' resolve in risk mitigation and problem solving. When things go wrong, how do you stay cool and tackle the challenge at hand? And these are the exact problems that students will have to face as they progress into the space industry, or any industry for that matter, is things don't always go wrong. Sorry, things sometimes go wrong, things don't always go right, just like that sentence. It's all about how do you recover, how do you stay cool, and how do you work effectively as a team, as nothing can be completed by no individual. And this is an absolute thread, millimeters away from going out of bounds right there. Let's see if the rover team, the University of Melbourne rover team, can recover from this tricky position as they're sandwiched between the outer boundary of the grounds and the lander, whilst holding a sheet of pavers. This is quite a tricky maneuver. The base station team can call an intervention, or the field team can hit the emergency stop, which is that big red button sitting on the top of the rover that every school child wants to press. And if they do, that ceases all power to the rover and immediately ends the task, whereas an intervention called by the base station team gives a 10% penalty haircut to all points for this task, but allows the field team to intervene and perform some basic maintenance on the rover. And looks like they may require neither of those as they begin to recover with just about 20 minutes left on the clock, with a task finish time at 12:55. They're sitting on a nice 5 points. Can they get any more points for this task? They've got 3 activities up for grabs: clearing the debris, constructing, and excavating and depositing. I just want to remind everyone, this challenge is made possible by our lovely sponsors, enabling students from around Australia and international teams hailing all the way from Poland. 8 rover teams competing today across 4 tasks, across 4 days, enabling students the unprecedented opportunity to practice real-world scenarios that you can't practice anywhere else on a simulated lunar surface with rovers as part of a mission. And this is what dreams are made of. Many researchers around the world don't even have access to facilities like this, so the students are really practicing something at a research high academic level, seeing how their integrated systems, and I'll remind everyone watching and spectating across today and the other days that these systems are designed and built on extremely tight budgets in very busy workshops around Australia and the world by undergraduate students who are also juggling full-time study and part-time work. So everything you see here today, and I mean everything, is designed and built often by very sleepy students. And with about 20 minutes left on the clock, let's see if these small maneuvers will allow them to save points. And this is very much like the Hayabusa mission by the Japanese Space Agency, where they had to perform a series of maneuvers to try and land on a comet. That's right, we've sent a lander which retrieved material from asteroids and comets out in deep space. We've returned that material back to Earth, and we've already done some analysis on it, showing the presence of some basic molecules essential to the formation of life, potentially here on Earth. And let's see how the rover maneuvers this tricky position. This is an excellent demonstration of the issues with the forces generated by the rover, the tow force. Moon, the gravity is 1/6 that of Earth, which means that the rover has less mass to weigh itself down on the surface, meaning that the amount of leverage or traction it can generate on the surface is reduced. And when you're towing a series of pavers covered in sand, sometimes that force is greater than that which the rover can generate, leading to issues like you've just seen. And these are real-world issues that many rovers will have to face in the future. Is how do you generate enough force to dig through the regolith, make your way through, and how do you do so efficiently in terms of the amount of energy that you expend trying to excavate that material. And if we can get a close-up of the rover, some of those astute will notice the robotic arm perilously close to the e-stop. And you may wonder, has a rover ever hit its own e-stop? Yes, it has. I've seen it firsthand. And right there you can see the plastic from this scenario with just about 15 minutes left on the clock. And up on the screen right now you can see the base station, the rover antenna used to communicate with their base station, with several different cameras feeding a live stream back to the base station operators. And the issue that many operators will find firsthand is, as well as during the design and development of the rover, is how many cameras do we need? Where do we put those cameras? What are the most required views that we can use as rover operators to figure out where is the rover happening? And this is something that there's no right or wrong answer, and it depends on the rover operator as well. Sometimes you need a rover camera right at the front for hazard avoidance. Other times you need a bird's eye view so you can see where are the wheels in relation to obstacles. Sometimes you need a rear view camera to figure out if you reverse, where will you go and what will you hit? And for those more complex systems, you can even put cameras on the end of your robotic arm to figure out where are each of the joints in space, to figure out and to assist with interacting with the environment, much like the rovers did yesterday as part of the post-landing task, where the rover had to download some instructions, some maintenance instructions using RFID, which is the same technology as the swipe key cards that you use to gain access to buildings, and then to perform some maintenance with its robotic arm on the control panel of the post-processing plant, which you'll see up on the screen. And the current view right now is the base station operators using those joysticks to try and reposition the robotic arm into a favorable position to try and recover the pavers left on the surface. And this is just highlighting the need for end stops and safety parameters and homing so that when things go wrong, you can recover quickly. And this highlights some of the important practical issues of not only do teams of undergraduate students need to design and build their rovers, they need to fly them interstate or overseas to come and compete, but they also need to have lots of practice with operating those rovers under competition conditions. Robotic arm right now repositioning itself, moving in every direction. Looks like it has several degrees of freedom, and each degree of freedom is its rotation about an axis. So often you'll have a shoulder joint rotating on the base with an elbow or wrist joint. You can see the rover little wave to the audience right now. With each degree of freedom comes increasing complexity, as how do you operate a robotic arm in three-dimensional space with no reference point? Often you're controlling these robotic arms with Xbox controllers or joysticks, which isn't very intuitive unless you have lots of practice. Some novel solutions I've seen is the development of a tiny little toy robotic arm used by base station operators, which they move to activate as a feedback mechanism to control the arm in three-dimensional space. This is really handy if you're trying to figure out where are all the joints, so that if you need to pick up an object on the ground, you're moving in the correct axes for the robotic arm so that it's efficient. But that comes with lots of issues in terms of how do you design that system so it's robust. And it looks like the rover is jetting into the debris clearing area to try and clear some of that debris. Each piece is worth, I believe, 5 points. No, sorry, 4 points, 5 pieces each. And they need to clear that debris across that blue finish line, spray painted in lunar blue. They've got about 11 minutes left on the clock. To have ever played on the beach with a sand shovel, right now you're seeing what playing on a lunar beach would be like, remotely controlled via a lunar rover out there on the lunar surface. Each piece of debris, if they manage to get it across the line, will get them some points on the board. And again, this is no simple task. For those who have never operated or worked with a rover or robotics, this is not as simple as plugging in and turning on an RC car, a remote controlled car, and pressing go with the controller. These are complex and hand-built systems by these undergraduate students, where everything from the foundational code used to drive and control the motors down to the communications protocols and the design and development of sometimes their gearboxes and viewing systems are all designed and built by students. It's incredible. And up on the screen right now, you can see that narrow pathway between the two valleys. Sorry, between the valley walls, the debris embedded into the surface of the ground, the rover trying to use that shovel to try and clear it out of that area. And this is a real world scenario that rovers may have to complete on the lunar surface, as there is rocks scattered across the surface acting as serious hazards to the traversal of human astronauts and robotic rovers. And one of the key or core activities of any Foundation Services rover is the preparation of the surface for future human activities. And when you're running across the surface at 1/6 the gravity, it's easy to fall. And I recommend checking out YouTube videos of the Apollo astronauts, as they were always falling over. They look like babies running across the surface, learning how to walk for the first time. Seven minutes left on the clock at 12:55, the end of Uni Melbourne rover team's time on the lunar surface pitch. You can see up on the screen right now the rover midway in that allocated debris clearing area marked by the blue spray paint. Their job, for a total of 20 points up for grabs, is to clear each of those pieces of debris, those 3D printed black cubes, from that area. And this is to represent a real-world challenge that a Foundation Services rover, much like the Australian Trailblazer rover recently announced, will have to perform in terms of clearing a path, literally and metaphorically, for future human explorers. Huge round of applause, please, for the University of Melbourne rover team, as they've called the end of their task, end of their attempt. Phenomenal effort, facing all kinds of complications, dragging their paver solution across the surface and waving to the audience with almost 2 wheels up in the air at one time, and almost hitting their own e-stop with a robotic arm. Truly a testament to how complex these systems are. Phenomenal effort. And up next, I believe we are on a lunch break until 1:45. So at 2 p.m, we have coming up next the University of Technology Sydney UTS rover team, followed by 2:45 Queensland University of Technology QUT. Then at 3:30, we have Project Scorpio hailing all the way from Poland, our first international competitors. And last but not least, we have at 4:15 p.m, the University of Adelaide rover team, with the final attempts, first and only attempts at the excavation and construction task for the Australian Rover Challenge. The local time is 12:50. The weather is cloudy, and hopes are high to see who can score the most amount of points for these tasks. The current leaderboard, I believe, is Monash University at number 1, followed tightly behind by University of Melbourne and Project Scorpio.
Australia is a nation of creators, aviators, protectors and innovators. From aviation's first light to the dawn of the jet age and beyond, at Boeing, we're building the future together here in Australia. Inspiring those in pursuit of new frontiers, connecting, protecting and exploring our region and the world. Home to the broadest aerospace portfolio in Australian industry, powered by talented, dedicated and diverse teammates. Delivering manufacturing excellence, building composite aircraft parts for the world's most efficient airplanes, using advanced robotics, materials and digital technologies. Never compromising on safety or quality, always focused on sustainability. Solving tomorrow's problems today with Australia's leading researchers, scientists and universities. Developing new military platforms and communications networks and helping ensure they are always mission ready. Keeping customers airborne by providing the services they require. We stand shoulder to shoulder with Australians during natural disasters, on the front line and in peacetime. We support veterans and our community, and we nurture the next generation of aviators to excite, to be bold. Boeing Australia. Made in Australia by Australians for the world.
Okay, are you ready? The first university to admit women, 2 Nobel Prizes, then another, then a couple more, 12 knighthoods, 22 Olympians, a pack of COVID-sniffing canines, Australia's first female Prime Minister. Finally, treatments for diseases and other scary things, the first female Queen's Counsel, Supreme Court Judge and State Governor, all in one, first in the family with a degree, a black belt, a robot. First Aussie to walk in space, helped detect gravitational waves, made lots of babies, world top 100 in all this stuff. Launched a satellite, revived lost languages, home to 1600 brainiacs, and a winery, all in the heart of Australia's most livable city. So, what's next? Make history at the University of Adelaide.
1, 2. Just checking range. Check 1, 1, 1, 1. Check 1, 2. Wah, wah, wah. Range to over here. Check 1, 1. Dan, can you hear me clearly where you are right now? Thank you very much. Check.
Australia is a nation of creators, aviators, protectors and innovators. From aviation's first light to the dawn of the jet age and beyond, at Boeing, we're building the future together here in Australia. Inspiring those in pursuit of new frontiers, connecting, protecting and exploring our region and the world. Home to the broadest aerospace portfolio in Australian industry, powered by talented, dedicated and diverse teammates. Delivering manufacturing excellence, building composite aircraft parts for the world's most efficient airplanes, using advanced robotics, materials and digital technologies. Never compromising on safety or quality, always focused on sustainability. Solving tomorrow's problems today with Australia's leading researchers, scientists and universities. Developing new military platforms and communications networks and helping ensure they are always mission ready. Keeping customers airborne by providing the services they require. We stand shoulder to shoulder with Australians during natural disasters, on the front line and in peacetime. We support veterans and our community, and we nurture the next generation of aviators to excite, to be bold. Boeing Australia. Made in Australia by Australians for the world.
Okay, are you ready? The first university to admit women, 2 Nobel Prizes, then another, then a couple more, 12 knighthoods, 22 Olympians, a pack of COVID-sniffing canines, Australia's first female Prime Minister. Finally, treatments for diseases and other scary things, the first female Queen's Counsel, Supreme Court Judge and State Governor, all in one, first in the family with a degree, a black belt, a robot. First Aussie to walk in space, helped detect gravitational waves, made lots of babies, world top 100 in all this stuff. Launched a satellite, revived lost languages, home to 1600 brainiacs, and a winery, all in the heart of Australia's most livable city. So, what's next? Make history at the University of Adelaide.
Hello and welcome back to the second half of day 2 of the Australian Rover Challenge here in beautiful, sunny, not so cloudy Adelaide. My name is Daniel Ricardo and I'll be your MC for today. Right now at 2 o'clock, we've got the excavation and construction task for the University of Technology Sydney, UTS. They've got an allocated 40-minute slot finishing at 2:40, where they will need to complete one of 4 activities for a total of 100 points. You can see up there on the screen right now. Descend down the ramp, that is all 6 or 4 wheels. All of their wheels, hello. All of their wheels touching down on the ground to get the 5 points. Then 20 points up for grabs for clearing the debris from the field. And this is an actual task that Foundation Services rovers will have to complete. to create a clearer path for humans and other rovers to navigate across the surface. Then we will have, or available to the teams to complete, is 40 points up for grabs for the excavation and deposition task. This involves the rover excavating regolith from the regolith acquisition zone, which should just be off to the side of your screen right now, depositing that regolith into a hopper, a metal hopper, just to the right of the screen, just here, next to the processing plant. And teams will be awarded points based on the amount of regolith that they deposit into that hopper. The team with the most massive material gets the full 40 points, and teams get scaled according to how much regolith they deposit in there. And last but not least, the construction task worth 35 points, designated by the blue spray-painted area right there on the front of the lunar surface with the smiley face. This is challenging teams to design their own dust mitigation solution, where the rovers will deploy their own road, drive over their road, and then get points based on how many pavers or individual pieces are in full contact with the ground at the end of the challenge, and they get points based on the amount of pavers covering that area, which is a 1.2 by 2 meter rectangle. So far, we've had about 4 teams competing. No one has gotten all 100 points yet. And much like yesterday's the Australian Space Agency post-landing task, no one has yet to achieve all 100 points for any task. This is highlighting just how difficult it is for these challenges that we as judges have set out. We're really pushing these undergraduate students to come up with novel solutions to these challenges. And up on the screen right now, you can see the University of Technology Sydney, UTS, weighing in their rover. I believe it is made of carbon fiber tubes together with nylon, 3D printed nylon connections. It is extremely lightweight, extremely nimble. I saw it zipping around on the surface last night in practice. Let's see how University of Technology Sydney perform here today on day 2 of the Australian Rover Challenge. And intermittently up on the screen, you will see the leaderboard for the 8 teams coming from all across Australia, several states, as well as one team all the way from Poland, our first international competitor. Hello, Project Scorpio. And you can see right now, number 1, having completed both tasks so far at a score of 224.6, Monash Nova Rover from Melbourne, followed closely by University of Melbourne Rover Team URT at 151.4 points, Project Scorpio at 135.8 points. They have yet to compete. They will be competing later today to see if they can take that number 2 or number 1 spot off the Melbourne teams. Then followed closely by the Queensland University of Technology Rover Team on 119.2 points, Adelaide Rover Team, UQ Space, UTS, and RMIT. These leaderboards will be updated as the day progresses and are available on the Australian Rover Challenge website for those interested in exact point scoring. Please check it out, and you'll stay notified if you're interested in competing in next year's 2024 Rover Challenge, the 4th installment. Of course, the allocated task start time was 2 o'clock, so the team are eating into the available minutes that they can complete these activities. They've got 40 minutes on the clock from 2 to 2:40 p.m. to complete to complete 4 of available 4 activities. And I'll remind everyone up on the screen right now, descend down the ramp, clear some debris, excavate and deposit some regolith, and lastly, construct a dust mitigated road. Now, you may be asking, Daniel, why do we need to do these things? Well, as we transition onwards to the lunar surface as part of the Trailblazer mission, Australia's participation in NASA's Moon to Mars initiative, Australia, as of, I believe, 3 days ago, recently announced the winners of the Trailblazer grant, where 2 groups of Australian companies will design and develop a prototype lunar rover, with the winning group being selected to be fully funded and send an Australian rover to the moon. How incredible. I believe this will be a signature mission that will herald a new generation of space enthusiasts and to show school children and students, young and old, across Australia that we are going. And as NASA likes to say, we are going to stay. Sending human astronauts back to the moon in the next couple of years. We are sending the first woman and next man as part of the Artemis program, the sister of Apollo, the next several years. And Australia's role in that initiative is to send a lunar rover. And what you see before you today is a simulation of that task. And we are training the next generation of Australian space industry to, in real time, participate in exactly what that Trailblazer mission is going to do. And this is includes the task you see before you today. Excavating regolith, which is a fancy word for extraterrestrial soil, from the RAS, the Regolith Acquisition Zone. And this is, word for word, as in the RMIT for the Trailblazer Stage 1 and Stage 2 grant. Rovers will then excavate regolith, deposit it in a hopper, and on the lunar surface, this will be a NASA payload built and designed to extract oxygen from the regolith. And this is part of the broad term of in situ resource utilization, ISRU. It's a buzzword that everyone likes to use, but it's really important and critical to the future and sustainability of space exploration, because you cannot simply launch everything up with you into space, because that's expensive, complex, and a waste of resources. Instead, we will do things like using resources in situ. In situ is a fancy word for right there in space. So you can do a lot of things with lunar regolith. You can do a lot of things with regolith on the surface of any extraterrestrial body, which is a pile of rubble, ice, and rock, or an asteroid, or even the surface of Mars. And regolith is just simply a fancy term for the crushed up, extremely fine-grained rock, which is essentially sand, depending on the grain size, that covers the surface of these planets and moons. Regolith is extremely difficult to work with. The dust portion, so the extremely fine dust-sized particles of the lunar regolith, is the single most biggest hazard to the future of Artemis and any surface mission. Why, you may ask? Because that lunar dust can be smaller than the particles that make up smoke. And those particles are essentially extremely jagged, tiny pieces of glass and rock that have been pulverized over billions of years by micrometeorites, because the moon doesn't have an atmosphere. So meteorites here on Earth burn up as they graze across the skies. That's why you see fireballs in the sky. But on the moon, that doesn't happen. They slam directly into the surface, creating craters and crushing up the surface over time into smaller and smaller fragments. These jagged pieces of particles, because there's no atmosphere, can become electrostatically charged by the radiation from the sun and interstellar objects, blasting across the surface, charging it, and causing that dust to levitate. Yes, levitating dust. These levitating dust particles can go up to 10 meters off the surface, and this was witnessed firsthand by the Apollo astronauts who went to the moon back in the late 60s, early 70s, as the sun rose across the horizon, or set, depending on the time, actually created observable sunsets as the light refracted through the dust, levitating off the surface, creating an incredible sunset that humans may yet see again in the next few years as they return back to the surface as part of the Artemis program. And here today, undergraduate students will be sending their rovers to compete on this simulated lunar surface. And as we're approaching the 2:10-minute mark, University of Technology Sydney have 30 minutes left on the clock to get their rover on top of the lander and to get things functioning. And I'll just remind everyone watching the live stream today, and for those here, spectators, thank you for coming down. This is not as simple as driving an RC car. When you see the rover, that doesn't mean that the rovers aren't complex, sorry. It means that the operation of these rovers is extremely intricate. So these rovers are designed and built by undergraduate students. No one teaches you how to build a rover in university, so they've done this on their own, from scratch, in their spare time, in addition to full-time study and part-time work. And I just want to bring attention to the huge success of several of the rover teams today, achieving what look like simple tasks are incredibly complex. The accumulation and the result of sometimes years of hard work, several, if not many months and days of restless nights, staying up late in the university workshops, trying to get these things up and running. And these teams are comprised of students from across different faculties at different universities. And this is one of the things I love about the Rover Challenge, is that You're not limited to engineers, you need scientists, you need economists, you need business people, you need arts, you need people studying humanities. As we're going into space, as we want to send humans into space, we need to send all of humanity with them, which means if you're interested in space, there's a role for you too. No matter what you study, no matter your background, no matter where you come from, you have a role to play as we go onwards to the moon and later to Mars. At 2:12 p.m, the team has, I believe, 28 minutes left on the clock. Task time finishes at 2:40 p.m. Every team has an available 40 minutes on the clock to complete 4 different activities as part of this task. You can see right now up on your screen the University of Technology Sydney UTS rover up on that lander. It's an incredible complex piece of machinery made of carbon fiber tubes together with nylon interlocking pieces. It is extremely lightweight, extremely nimble. I saw it zipping around yesterday at practice at the night. And you can see mounted on the back, right now you can see the base station. And I remind everyone, as the teams come out here to compete, they split into 2 groups, a base station group and a field group. And it's the base station job to receive the input from the video cameras and all the data streams from the rover to control it remotely. And they do this purely through the screens they have available to them and the information received wirelessly via their antennae. So there's no input between the field team and the base station team. And this is to simulate what an actual mission control would be like during a mission to the moon. You have a contingent of staff working on Earth in the ground division. And although on the moon you wouldn't have a bunch of technicians up there, but here today, as part of the Australian Rover Challenge, in the case of an emergency or intervention, we do have field staff or field crew here ready to step in. And when they step in, if a base station individual would like to call an intervention, the base station team can step in, perform some quick maintenance. However, the team takes a 10% haircut to points for that task. So not only do team members need to design, build and operate these rovers, once they come to competition, they need to think about strategy in terms of when should we call an intervention? Do we need to call an intervention? Which task do we do first? What is the sequence of those tasks? How long do we spend on each task? How do we maximize points? And at the same time, how do we keep the rover safe? Sometimes the maximization of points means putting your rover in danger. And again, that is risk mitigation and risk management. Problem solving on your feet. And these are the real world scenarios that students will have to face when they go into the workforce. Nothing always works. And what matters is, as leaders of those teams, how do you ensure that everyone remains calm, cool and controlled, and everyone has a role to play in fixing and addressing that fact? So not only are we training or giving the opportunity for scientists, engineers, participants of all these rover teams, we're also training the leaders that will lead these teams to amazing, glorious new missions onto the moon, onwards to Mars, and even to deep space. One little fact. So up on the screen right now, you can see the base station crew working on wooden trestle tables with lots of space. I used to be part of a rover team that competed over in the US as part of the University Rover Challenge out of the Mars Desert Research Station, hosted by NASA. And that was a simulated Martian mission. And the base stations that we got to use were the back of U-Haul trailers that you couldn't even stand up tall in. So you're in a small little trailer out in the middle of the desert trying to operate a rover. And here, down in Adelaide, we have large, luxurious tents. How lucky. And an update on time, it is 2:16. The start time for UTS was 2 o'clock. Finish time, 2:40. They still have yet to descend down the ramp. And I'll bring everyone's attention to, again, just how difficult it is to operate these rovers under competition conditions. Just getting it moving and driving is one of the biggest hurdles in of itself. So as soon as that rover gets even a little bit of movement, I want to hear a huge round of applause as UTS have almost entirely redesigned their rover chassis. They've done a huge amount of work, as is every team in the space of less than a year. And these students are working hard and getting trained in this amazing opportunity to take what they learn at university and apply it to real-world practical issues. And I hope that's one of the key outcomes of participation at the Rover Challenge, and one of the reasons why I really wanted to start this challenge is that taking what you learn from university and getting the experiences so that when you go out into the workforce, you're ready to go. And participation in the Rover Challenge is always available for those listening on the live stream or those with children or those undergraduates present today. We're not going anywhere. We'll be here again next year and for all the years to come as we continue to expand out the Rover Challenge team list to more universities around Australia as well as overseas. And again, another huge shout out to Project Scorpio, hailing all the way from Poland as our first international competitors. They're currently ranked 3rd out of an available 8 slots, and with 2 tasks left to go, let's see how far they can go in showing the Australian teams just how serious Poland are. They're definitely a force to be reckoned with. And for those watching, the start time of the task does not start until the base station and field team are in agreement and initiate to judges that they would like, or they are ready to start the task. So during this setup time, the base station and field team are allowed to walk over to the rover and set up and interact with it. But once they say go, the base station team gets sealed off. They get no more information from the outside world, and they are running completely, not quite blind, but definitely entirely through the rover, through the communication systems that they've established. And this, again, goes back to some fundamental questions of what do you need to see and how do you get that information? What information do you need to control the rover? Do you have a live stream of the power being drawn on by the wheel motors? Do you need the height? Do you need the tilt and yaw of your rover? Is it going to tip over? How many cameras do you need on the rover? What's the bandwidth of those cameras? Do you need high resolution, high frame rate, or can you get away with, a few pictures every now and then? How many cameras do you put on your rover, and where do you put them? Do you need to see the front and back, or can you just put one on top and have a bird's eye view? And again, because this is a novel engineering challenge, there's no right or wrong answer. And one of my favorite things about participating in rover challenges is you get to see the novel approaches from students across Australia and now across the world of how they tackle these questions, these fundamental issues. No rover is the same, and that's one of the beautiful things about the Rover Challenge is that you get to see out the back as the teams are testing and iterating upon their rover, they get to talk to each other and mingle and learn about the different approaches, the different design considerations, the different ways they were taught how to design and build and work together. And that's the beautiful thing, and one of the purposes of the Rover Challenge is not only providing an opportunity for students to design and build rovers, but to build a community, a sense of we're all in this together. And just to symbolize that fact, the winners of the Rover Challenge, first, second, and third place, all receive a trophy. And we don't buy or build this trophy ourselves, the students build it. And what do they build it out of? Well, they build it out of all the failed 3D prints, all the exploded Arduinos and Raspberry Pis, everything that broke or failed during the development of the rover. And this is to symbolize the fact that and just a quick update, the time is 2:23. The end time is 2:40 p.m, so they've got about 17 minutes left on the clock, and I have been informed that the base station has signaled that they are ready, so at any moment that rover is going to take off. And when it does, I want to hear a huge round of applause for the University of Technology Sydney UTS rover team coming down to compete in the second task out of 4 available tasks for the Rover Challenge. And of course, this is the excavation and construction task, comprised of 100 available points out of a total of 500, broken down into 5 what seems like simple but incredibly complex activities. Activity number 1 is descend down the ramp for 5 points. All wheels need to make complete contact with the ground. And then they can complete these activities in any order, but you can clear some debris for 20 points, perform excavation and deposition of regolith for up to 40 points, or construct a dust mitigation road for 35 points. And the way those are scored is the team that deposits the most amount of mass, or the total amount of regolith into the hopper, wins the top 40 points, and every other team is scaled against them. So it's really creating this sense of competitiveness and game theory of how much material do we need to deposit? How much time do we spend on that activity? What other activities can we do? And this raises some interesting questions of, this is what a mission planning team will have to do if you're conducting a surface mission on the moon or Mars, is no one tells you what to do, you need to figure it out. And there are risks associated with every decision, and it's your job to work with your team to think about how can we conduct the most amount of research with our rover, but how do we do it safely so that the rover mission doesn't end prematurely. And a perfect example of that, by no means of themselves, is as part of the NASA Mars Exploration Rover, or MER, Spirit and Opportunity, back in the early 2000s. Spirit, as part of its mission, got prematurely bogged down in a cache of really thin, almost behaving like flour, mineral called jarosite. And as it drove into that patch of loose material, essentially quicksand, it got bogged so much that it got stuck there, prematurely ending the mission. But did that stop the mission? No. The rover had a robotic arm and managed to conduct several hundred sols, or Martian days, worth of research by investigating the immediate surrounding area of where it got stuck, and continuing to provide a lot of important information about the surface of Mars and the evolution geologically and environmentally with time. And for those interested, why are we sending rovers to the moon in the first place? Well, to send humans is an incredibly dangerous and expensive mission where if things are being rated for human spaceflight, they must require an extraordinary amount of redundant safety systems and mechanisms. Whereas if you send a rover, you're not putting human life in danger, as well as a rover is much less expensive and complex. So a lunar rover also enables compared to a lander, such as the Viking 1 and 2 landers, who were the brainchild of Carl Sagan. So Viking 1 and 2 were sent to Mars to search for evidence of extraterrestrial life, so astrobiology, astro being space, biology meaning life, so life in space. However, those landers were limited because they were stuck in one position, whereas a rover allows you to navigate, to drive around, to go look at that rock over there that looks really interesting. And the Mars exploration rovers, Spirit and Opportunity, their job were to be, essentially, geologists. So they were equipped with a suite of different instruments and sensors and cameras so that they could go and look at the rock and the geology to learn about how the surface of Mars has changed with time. And this is something that I like to do because I'm a geologist and I like looking at rocks, is how can you use the geology around you to, like a book, learn about the history of that surface or that environment or that planet and moon. And this is something that the lunar rovers are doing right now, such as the Chang'e rovers from the Chinese Space Agency, is returning samples back to Earth from the moon, which is no simple feat, to look at the material, that extraterrestrial regolith, to see how does that change with depth. What is the mineralogy? What is the chemistry? What is the mechanical behavior, the particle size and shape? And just as a reminder, the lunar regolith is essentially small, tiny pieces of jagged glass or crushed rock that have been pulverized by meteorites over billions of years, and with no atmosphere on the moon, or basically a negligible one, or also a negligible magnetosphere, it means that radiation slams right into the surface together with micrometeorites, which just means meteorites on the order of a few microns or a few centimeters. And those unique space weathering phenomena, so weathering being such as the wind and rain that erodes rocks here on Earth, the moon and Mars has space weathering, which means that the sediment that is created on the moon is extremely unique. And this is one of the reasons why designing systems for these unique environments is incredibly complex, because not only do we know little to nothing about these environments, as we've only landed on the moon a handful of times, it means that as we design systems, much like these students are designing rovers for a competition environment that they don't get to experience until the day of, you don't know if it'll work until it gets there. So this is why testing and development is so important. And just an update as well, it is 2:29. We've got 11 minutes left on the clock for the University of Technology UTS rover team to get some points on the board. All they need to do for the first 5 points is descend down the ramp . And for those present here today, just a little interesting fact as well. You'll see that the sun is beginning to come out today after a very cloudy day. And as it sort of bisects the arena with one part being illuminated and one part being shaded, this raises the interesting point that depending on where you are on the moon, the illumination conditions change dramatically. So the moon orbits on a single axis, or perpendicularly on its axis, which is just as simple as if you were to spin a basketball on your finger, that's how the moon orbits. It doesn't have a tilt, which means that if you're on the equator, sunlight hits it almost perpendicularly, so straight on. This means that the surface temperatures can go up to 400 Kelvin, which means several hundred degrees during the day. And of course, a lunar day is about a month, being the lunar cycle. And then at night, as the sun sets over the horizon with no atmosphere to insulate the surface like we do on Earth, the temperature drops down in a matter of hours, sometimes minutes, down to less than 100 Kelvin, so extremely cold, cryogenic. What does this mean? Why is that important? Who cares? You may be asking. Well, if you're on the surface and you go from several hundred degrees hot to several hundred degrees centigrade below zero, that's tricky to survive in, especially if you're a human, especially if you're a rover. So not only are you designing systems for extremely high radiation, ultra high vacuum, high temperature environments, they also need to be equipped with heating elements to keep them warm, or the electronics warm, during the cold night. And this is a real-world scenario that NASA, as well as several private companies, are trying to tackle right now as humanity seeks to explore a region we've never gone before, the poles of the moon, And because the poles of the moon are at the poles and the moon rotates perpendicularly on its axis, that means any topographic depressions, like a crater at the poles, never receive direct sunlight. That means these regions, which we call persistently shadowed regions, PSRs, can remain dark for billions of years. And this is something that I'm doing as part of my PhD, is investigating the material that freezes here, the icy lunar regolith. And the reason why is because there is water at the poles, and water is essential for spaceflight. It keeps humans alive as it gives us drinkable water. It allows us to grow food with agriculture, and you can use it for a range of different processing methods, such as making construction materials, or in the process of making bricks, making wire. And these PSRs can get so cold because they're so dark, and they remain dark for billions of years. We've actually recorded the coldest surface temperature in our solar system in the bottom of a PSR, 25 degrees above absolute zero, so 25 Kelvin. Not only is that cold, that's extremely cold, so cold in fact, if we were to drive into that region, and this is a question that I'm trying to address as well, is what happens to the environment, so those PSRs, if you drive a rover in there? So your rover may be operating at a couple hundred degrees centigrade because electronics need to stay warm to operate. If you have a rover that is relatively extremely hot, driving into a pristine environment that is around 25 Kelvin, or at least below 100 Kelvin, what happens? Sort of like a hot knife through butter, will your rover just sink through the material? And then this raises some interesting ethical questions, such as, should these PSRs, or surfaces on the moon, be considered national parks? What is the boundary for the landing zones for the Apollo missions? Should those be considered national treasures in sort of history? It's a key point to understand the universe. Much like the Wright brothers' first flight, our first mission to the moon should be recorded. And that raises questions of, what are the boundaries? How close can we get to those landing sites? So as we attempt to explore the permanently shadowed regions, for many students here today and for those tuning in over the live stream and around the world, you need to think about what are the ethical questions of driving into those environments and potentially causing irreversible damage, permanently transitioning some of the ices there, causing them to melt and preventing otherwise pristine environments from being explored by future generations. And these are the important things, and why spaceflight and space exploration is not just limited to scientists and engineers. We need people from every background, every culture, every discipline to have a say in how we explore, to make sure we do so sustainably for future generations, as well as safely for us now. And as a quick update after that spiel, it is 2:35. The UTS rover team have 5 minutes left on the clock as part of the excavation and construction task number 2 of the Australian Rover Challenge. And available 100 points up for grabs. And as a quick reminder, today we have the University of Technology Sydney. Then we have the Queensland University of Technology, QUT, starting at 2:45, followed by Project Scorpio, all the way from Poland at 3:30. And last but not least, 4:15 p.m., the University of Adelaide rover team, running on a skeleton crew after more than half of them got COVID. So they're really pushing the limits of how much can you do with very little. And once again, I'd just like to reiterate, the Australian Rover Challenge would like to thank and acknowledge all their sponsors for making this challenge what it is and scaling up every year. We've gone from 3 Australian teams back in 2021 up to 7 now, competing at least. We have many more around Australia ready to submit next year and get involved with the action. And of course, that action includes the Australian Space Agency post-landing task that we had yesterday, the excavation and construction task we have today, the iSpace space resources task that we have tomorrow, where rovers need to excavate icy regolith from the surface and then extract that as liquid water to give to me as a judge. And lastly, on Sunday, the Boeing Mapping and Autonomous Challenge, where rovers will need to navigate the surface and semi-autonomously or autonomously map the surface whilst avoiding obstacles out there which are limited, or which can include really real fake rocks made of polystyrene, some undulating terrain including crater walls, and the loose regolith that covers the surface that has been the bane of several teams so far, as many of them have become bogged down in that loose material. And just demonstrating, if it's this difficult here on Earth, just how tricky will it be on the moon? So far away with no technicians ready there to intervene and fix it. With 2 minutes left on the clock, let's see if UTS manage to get those 5 points up for grabs if they descend down the ramp. As well, I'd just like to shout out everyone watching home on the live stream, all the parents, friends and family watching, cheering on as these students compete here today in Adelaide. You make it all possible. Your support has enabled these students to come out here, compete after many, many sleepless nights, I can only imagine, trying to get these rovers ready for the competition. And with that, it is 2:40. So can I please get a huge round of applause, University of Technology, Sydney. And just as a quick reminder, again, this is not as simple as driving an RC car. You can't just turn it on, use the controller and press. For those on the live stream, welcome back. It is 2:47 with the start time for QUT being 2:45. The Queensland University of Technology are currently up with their rover to compete as part of the excavation and construction task number 2 of the Australian Rover Challenge. You can see right now up on the screen the Queensland University of Technology QUT-RC with their rover Artemis, hailing from Brisbane, Australia, with a total current score of 119.2, comprised of 59.2 out of 100 for the Critical Design Review and System Acceptance Review, CDR and SAR. And these are formal documents that all teams submit to us, the judges, during the development and design of their rover to showcase, is it ready? And does it meet the verification and validation criteria to compete at the Australian Rover Challenge? And then from those submission, you have 60 points as part of the Australian Space Agency post-landing task, which we had yesterday, where the QUT-RC rover team managed to snag 60 of the available 100 points. And today, their challenge, as part of the excavation and construction task, is to try and snag some more points. Up for grabs is 100 points broken down into 5 points for descending down the ramp, 20 points for debris clearing, 35 points for construction, and 40 points for the excavation and deposition of regolith. Overall, all these activities are meant to simulate the actual tasks that rover will have to complete on the lunar surface, which include preparing or clearing the way for human explorers and making sure that that smiley face in the bottom left right of the screen is covered by pavers. And this is part of creating a dust mitigated pathway so that when rovers continue to drive across the surface, they're not kicking up dust. And dust is a huge issue noted by all the Apollo astronauts, as the dust, the fine-grained fraction of lunar regolith or extraterrestrial soil, gets kicked up as humans jump across the surface or rovers traverse across the surface. This material stays levitated, hovering above the surface due to the electrostatic forces repelling particles, because there's no atmosphere, which means there's no wind or rain to take these particles out of this levitation. And this material gets everywhere. It gets into all the seams. It gets into the surface of all the astronaut uniform and spacesuits. This material is, and always will be, a huge issue that must be overcome.
Australia is a nation of creators, aviators, protectors and innovators. From aviation's first light to the dawn of the jet age and beyond, at Boeing, we're building the future together here in Australia. Inspiring those in pursuit of new frontiers, connecting, protecting and exploring our region and the world. Home to the broadest aerospace portfolio in Australian industry, powered by talented, dedicated and diverse teammates. Delivering manufacturing excellence, building composite aircraft parts for the world's most efficient airplanes, using advanced robotics, materials and digital technologies. Never compromising on safety or quality, always focused on sustainability. Solving tomorrow's problems today with Australia's leading researchers, scientists and universities. Developing new military platforms and communications networks and helping ensure they are always mission ready. Keeping customers airborne by providing the services they require. We stand shoulder to shoulder with Australians during natural disasters, on the front line and in peacetime. We support veterans and our community, and we nurture the next generation of aviators to excite, to be bold. Boeing Australia. Made in Australia by Australians for the world.
And welcome back to day 2 of the Australian Rover Challenge. Right now, we've got the Queensland University of Technology QUT rover team, whose start time for this task, excavation and construction, was 2:45. They're currently on weigh-in, so the maximum weight of the rover for this task is 60 kilos. Right now, they have remaining 30 minutes up on the clock left with a finish time of 3:25. Let's see if QUT can claim a top 3 position with up to 100 points available for this task, broken down into 4 key activities. I'll remind everyone, 5 points for descending down the ramp, clearing the debris, 40 points for excavation and construction, and 40 points for excavation and deposition, and 35 points for construction. This is one of the most complex and involved tasks of all the challenge, where the rover has to excavate and deposit regolith from the RAS, which is the regolith acquisition zone, deposit it into a hopper, deploy a road and then drive over its own road, and clear some debris. So there is a lot on the table for all the rover teams today. One of the biggest issues is time management and risk management, as we saw earlier, is how vulnerable can we make the rover to do what we want it to do? How far can we push it? With one team even almost turning off their own rover using the e-stop with their own robotic arm. I remind everyone, this is QUT's first attempt at the Rover Challenge. It's been less than a year from the start of the team to where they are now with a full rover. So every movement, every piece of point that they get here today is a testament to just how involved and dedicated these students are towards developing this rover. So my hat off to them, as I can tell you firsthand, building a rover in less than a year is no simple feat. 27 minutes left. You can see up on the screen right now in the base station, a dedicated control unit in a large Pelican case that has been developed by the QU team to control their rover. And this is an impressive amount of technology that they've developed purely for transporting around. And I'll remind everyone that these teams have come from interstate and overseas. And when you're transporting around a rover, you can't just pack that up into your suitcase. You've got to disassemble it, pull it apart, take it on a flight, which going through customs is definitely interesting. And then reassemble it and hope that it all works when you press go. Well, I would like to just shout out all the people watching on the live stream today. These teams you see before you do not represent the entire team, as many of the participants of these university teams are back in their host university states and towns cheering on the rover, as this is the culmination of sometimes hundreds of students' work over sometimes several years, as well as all the friends and family tuning in today. The rovers you see today are made up of, or they're the result of hard work of people, and you support those people in making this what it is today. So much like how the sponsors support the Australian Rover Challenge, you support and sponsor the students that create these rovers and make the Rover Challenge what it is today. So I'd just like to acknowledge all your hard work and dedication. And as we approach 3 o'clock, QUT have 25 minutes left on the clock. The start time, or the rover start time, is yet to be announced, to be stated by the base station team. So the base station team and field team are communicating currently via walkie-talkie, which you can see on the screen right now. There is an allocated window that every rover team gets to compete within, 40 minutes. However, the start time of the task does not start until the rover is up on the lander and the field team or base station team have initiated a start command. Once the rover starts, no field team is allowed on the pitch, and the base station gets sealed shut, and the only information that base station team gets is through the rover. So if things don't work, or you're driving blind, it's the quick thinking and troubleshooting of these teams as they practice getting these rovers to work under extreme conditions remotely. And I'll remind everyone that the base stations are actually at the back of the stands up on the screen right now in large tents. And this is to simulate the mission control, or the group that would operate a lunar rover back here on Earth. But on the moon, because it's so far away, there will actually be a delay of about 4 minutes. So you can't just simply drive a rover on the surface like you would an RC car. Instead, you would have to give it some commands, and the rover would have to execute those commands semi-autonomously. And this is the day in, day out work schedule of all the operators who work on, or who worked on, Spirit, Opportunity, the Mars rovers Curiosity and Perseverance. They work on a slightly different schedule, as the Martian day is about 20 minutes longer than an Earth day. So they download data each day from the Mars Reconnaissance Orbiter of where the rover is and what the rover's doing, and then give it a set of instructions. These instructions aren't always straightforward, because if you tell the rover to drive straight and there's a cliff in front of it, you better hope that the rover is smart enough to understand that there is a cliff and to override those instructions. And this is why semi-autonomous and autonomous traversal is so important, because we can't see what the landscape is like, and it is up to the rover to sometimes save itself. And this is, unfortunately, one of the issues that the Mars Spirit rover came into when it got permanently bogged down on the surface of Mars, preemptively ending the mission as it got stuck in a cache of mineral called jarosite, which behaves basically like flour. And as the rover drove into it, the wheels got stuck like quicksand, and it stays there. But that did not end the mission, as for several hundred sols afterwards, so a sol is a Martian day, that rover, that little rover that could continue to conduct scientific experiments and research on the surface with its robotic arm. And this is the troubleshooting and the quick thinking that people need to do here at the Australian Rover Challenge today is, as things go wrong, what can we do with what we have? How can we scrape every little point available to us? And that risk mitigation and problem solving are the real world skills that you can't practice anywhere else, and the things that employers really care about. It's not just what you know, it's what have you done? On the screen you just saw before, the base station operators using the joystick as part of the integrated and dedicated control system that these undergraduate students have built themselves to control the rover. It's a portable mission control in essentially a large briefcase that they transport around with them. This is a novel solution that several other university teams have actually used, that I've seen firsthand competing at the University Rover Challenge over in the US, where rather than setting up a keyboard, mouse and joystick, you just bring along a Pelican case, flip it open, and you've got your whole mission control right there. It is currently 3:08 with a task finish time at 3:25 for the Queensland University of Technology QUT rover team. This is day 2, activity 2 out of 4 available tasks. 100 points up for grabs today, and it looks like they're ready to safe two-person carry the rover over to the pitch. Some of you watching may be thinking, what can you do with 16 minutes on the clock? Quite a lot, actually, as I can attest to. Back when I was part of a rover team, we rolled in about 40 minutes before a task. We opened up the trailer only to see that our entire wrist had been shattered. So we had to perform an entire repair, replacing the wrist, getting all the control working, fixing all the electricals, all the hardware, starting almost 30 minutes late at our task. And within those last 15 minutes, we scored, I believe, almost 80 out of the 100 available points. So when you're working under stress, under pressure, I can tell you firsthand just how important it is to have a good team working with you. Everyone remains calm, everyone has a role to play. And how efficient, and oh, there it goes. That is the official start time for the QUT rover team. The base station has been sealed and the field team are not allowed on the field. With 50 minutes left on the clock, their first activity ahead of them is to descend down that ramp. 5 points are up for grabs once all 6 wheels make full contact with the ground. With 5 points right there. Fantastic job, QUT. Fantastic work troubleshooting. There it goes, taking its first steps across the lunar surface. The fact that it made it down the ramp and is traversing across the surface is a huge accomplishment. So, huge round of applause for QUT as they approach the regolith acquisition zone. 40 points up for grab right now. They may be using their robotic arm right there with a circular scoop similar to that as the NASA RASOR, or the RASSOR rover, which uses counter-rotating barrels to excavate regolith. The rover now is using its robotic arm and will attempt to excavate regolith from the RAS, from that pile of regolith just out of sight on the screen right now to the left of the field. And this is the exact task that the future Australian rover, as part of the Trailblazer mission, will have to perform. Excavating regolith from a RAS and depositing it into a hopper, into a NASA hopper, which will be a lander on the lunar surface as part of NASA's Moon to Mars initiative, where Australia will play a key role in demonstrating a Foundation Services rover, whilst NASA will be demonstrating the extraction of oxygen from the regolith, and this is achieved by heating up the regolith so that volatiles like hydrogen or oxygen are released from the regolith, demonstrating that we can in fact create breathable oxygen on the lunar surface just by heating up the soil. And this is quite a critical technology that I cannot wait to see more research and demonstration done. This is the topic of in situ resource utilization, or ISRU, and this is a topic that I'm studying as part of my PhD, which is how do we use the resources that we find out in space so we don't need to ship everything out into space with us. This means that less mass, less missions, less space debris, less complexity, and most importantly, it means that the technologies that we develop out in space have a knock-on effect that help us down here on Earth, because space exploration is all about efficiency. And I'd just like to remind everyone present here today, there is a free and public guest lecture or Make History speaker series here at the University of Adelaide titled Writing History in the Stars, hosted by John Coulton, who will be joined by Dr. Kimberly Clayfield from CSIRO, Dr. Sarah Cannard from Nova Systems, and Dr. Matthew Tetlow from Innovor to discuss how space science is addressing humanity's greatest challenges using satellite imagery. And this is going to address some really important challenges that lay ahead of us in terms of how do we track and monitor bushfires out in rural Australia and overseas, as well as tracking floods and hazardous events. How do we make sure that we optimize the use of pesticides or crop rotation in terms of optimizing agriculture, minimizing the use of pesticides, increasing the efficiency of when and which crops we harvest, as well as tracking the water quality of our river systems and lakes as part of the CSIRO Accra Watch program. So not only will you be able to track the weather, the sun and rain of your local city, soon you'll be able to track the water quality, and this is a program pioneered by CSIRO down here in Australia. So that will be hosted at the Braggs Lecture Theatre tonight at 5:30 p.m. It is a free event. Doors open at 5 p.m. Please come on down and listen to the fantastic insights of all University of Adelaide alumni. And I'll also point out to the student participants here today, I hope you had fun at the Animals Anonymous Australian Wildlife interaction, where some Australian native animals, including a crocodile, snakes, some birds, and a cute little quokka named Queenie, I hope you got to say hello to them. And at 3:15, the QUT rover team have 10 minutes left on the clock to try and get some regolith from the RAS. With just about 6 minutes left on the clock, the QUT rover team have called an intervention, allowing the field team to go and inspect and cause basic maintenance, communicating back to the base operators. In doing so, the intervention creates a 10% penalty for all points available to this task. And you can see up on the screen right now the 3D printed scoop attached to the end of their robotic arm, which rotates and drives that little opening through the regolith to try and scoop it into that barrel drum, whereby they'll rotate it the other way to try and deposit it into that hopper. You can also see the two large red buttons, the emergency e-stops that every rover must have as part of participation in the Australian Rover Challenge. These e-stops cease all power to the batteries and, if pressed, immediately end the task. The only people that can press these buttons are the field team. Right now you can see the field team trying to get into the internals of the rover, communicating back to the base station team. And I'll remind everyone that these aren't simply RC cars. The operation and control of all these rovers is done wirelessly, often through 2.4 and 5 gigahertz radio communication bands, which are the publicly available ones. As on the moon, there's no 5G, there's no wireless. You can't simply connect to EduRoam. You need to create your own communications network. And this is something that Nokia is actually planning to do, to deploy a 5G network as part of their upcoming mission to the lunar surface, where they will be part of one of the payloads deployed onto a lunar rover by a private startup in America, demonstrating the commercial lunar payload services, the CLIPS program from NASA, which aims to offload some of the burden of space exploration onto the private industry, where NASA awards grants to companies to perform tasks for them, such as SpaceX being the launch provider, Astrobotic being a service provider or a taxi from the SpaceX rocket to the lunar surface. You can think of this as catching a Uber and then a Didi, and then the deployment of a rover by another company, all making it possible so that if you want to send something to the moon, now you can for a small fee of a couple $1 million. So if you find some money behind the couch, let me know. As right now you can, I believe DHL allows you to send some items to a lunar post box on the moon. So if you want to send anything to the moon, you can do so right now. And with 2 minutes left on the clock, the intervention has ceased. Let's see if we can revive this rover to score some last minute points. And for those tuning in, it's an interesting thing how no matter at what stage you are in your career, things always go wrong. So today we have a wide range of talented undergraduate students, and I can confirm the rover is moving. With less than 1 minute on the clock, can they perform a miracle? And with that, it is 3:25. Let's give a huge round of applause to QT, managing to troubleshoot one problem after another and still get their rover moving. And as I was saying previously, no matter what stage you are in your career, things can go wrong, and I can testify to this fact. As part of my internship at NASA Ames a few years ago, I remember loading on some wheels designed and built by JPL onto a rover at NASA Ames. And when the rover tried to turn with those wheels, the wheels hit the chassis because they didn't measure the clearance enough. So really, even if you're a NASA engineer or an undergrad in your first year, it's okay to make mistakes as long as you learn from them and keep improving. So coming up next, hailing all the way from Poland, our first international competitor, Project Scorpio. And with a start time of 3:30 up on the screen, you can see Project Scorpio hailing all the way from Wrocław in Poland, currently sitting at a total of 135.8 points. I believe they're sitting third currently, 55.8 points out of a total of 100 for the CDR and SAR submissions. And then 80 out of 100 points as part of the Australian Space Agency post-landing task, a huge effort as their first attendance at the Australian Rover Challenge. Of course, this is not their first Rover Challenge, as this Polish team has done a circuit all around the world of Rover Challenges in America and Europe. And Australian Rover Challenge is one but many of a series of challenges around the world. And we are seeking to cement ourselves and make ourselves known as competent operators of lunar rovers as Australians, together as part of the recently announced Trailblazer mission, where Australia will send a fully Australian designed and built rover to the moon as part of NASA's Moon to Mars initiative, which will be landing on the moon sometime in late 2026, possibly 2027, depending on the development of the rocket. And the start time for this team is 3:30. They're looking good. They're positioned on the rover, ready to try and attempt all the activities that lay before them. And I remind everyone, for the excavation and construction task, they get 5 points up on the screen right now. 5 points for descending down the ramp. All four wheels need to make full contact. 20 points for debris clearing, which is clearing out the debris from the valley just on the lunar surface. Up to 40 points for excavating and depositing regolith into the hopper. 40 points awarded to the team that deposits the most mass of material at the end of the task, and the other team's winning a fraction of the points depending on how much mass they deposit. And then construction, where the team needs to deploy its own road, and you can see some of those individual pavers hanging off the back of the rover, the Polish team. And 35 points available for covering a 1.2 by 2 meter area with those pavers. And the purpose of this task is to try and get teams to demonstrate the construction of infrastructure like a road on the lunar surface. And this is a highly complex task only available to competitors of the Australian Rover Challenge, and I think it's the first time a rover has demonstrated this, where the rover will be creating a road to try and showcase how a rover could help with the issue of dust as it drives across the lunar surface and the surface here. It kicks up a small but not insignificant amount of dust into the air, and on the moon, because there's no air, there's no atmosphere, But because things are electrostatically charged, the regolith actually levitates, and the more material that gets into the seams and cracks of your rover, all the mechanical joints, all the rotations, the points of rotation, sorry, as well as once you get human astronauts there, that dust does not get away easily. It accumulates and accumulates, and slowly but surely wears down your system until the point of failure. So if we can reduce the amount of dust up in the air, above the surface, then you're extending the lifetime and operational functionality of your rover and that mission by orders of magnitude. Once that rover takes its first step off the lander, can I get a huge round of applause? At 3:30, the start time for this task, or the available time, has started. This team has 40 minutes. So from 3:30 to 4:10 to complete one of those four activities. And you can see on the screen right now the security cam providing a nearly 360-degree view, or should I say 180 view, of top-down bird's eye view of their rover with a 4-wheel system on a bogie drive. Each of those wheels covered in a unique fabric that has definitely seen some wear. You can see the cuts and open holes on the wheel, showcasing that this team has tested to a high degree. And this raises an interesting point of there's no right or wrong way to design a rover, and the range of approach or design approaches from each of the teams is extremely varied. Some teams have 4 wheels, some have 6, some have skid steering, which is similar to how your car drives. Other rovers have individual pivot steering for each wheel, meaning you can pivot on a dime. Some teams have large 3D printed wheels with huge grouses, which are the fins that cover a wheel. Other teams, like this, have fabric. And again, there's no right or wrong way to design. As long as it works, hey, it works. And that's what it's all about. Round of applause as the rover takes its first step down the ramp. As all 4 wheels make contact with the ground, that awards 5 points, part of activity 1. And now it is up to the base station operators to operate on their own with no information from the outside world except the information coming through on the live stream of that camera, or several cameras on their rover, as well as the input or the sensor data coming from their wheels, the odometry, and the Jetson that may be powering their rover. And it looks like the first activity that they will attempt is the construction task, the deployment of those pavers being currently cradled by the robotic arm on the surface or the top surface of that rover. If they successfully deploy those pavers, they can be awarded up to 35 points for covering that 1.2 by 2 meter area. And I remind everyone, the purpose of this activity is to showcase a rover deploying its own infrastructure. And one of the novel things is, as we were designing this activity, we wanted the teams and students within those teams to think about how can we do this within the weight and size constraints of the task. Oh, and an amazing little deployment mechanism. As part of this task, the rovers, including all the pavers and all the systems on board, have a total mass budget of 60 kilos, whereas the other tasks had a mass budget of 50, with the overall combined mass of everything that the team brings with them to compete being less than 80 kilos. The maximum dimensions of the rovers are 1.6 meters in every dimension. And this is trying to get students to really think about how do we optimize what we can do with the mass budget that we have available to us. And when you go to the moon, rovers, or sending rovers on the order of 10 to hundreds of kilos, is incredibly expensive. So the NASA Mars Curiosity and Perseverance rovers currently on Mars weigh about a ton, or equivalent to a car. And I can tell you that launching a car from Earth to somehow land on the surface of Mars and remain functional is not a simple task. And with 5 minutes through the task already, the team is making good time in their first attempt of this activity, construction. 35 points available up to them. The only other team who has attempted this task successfully is the Monash Nova Rover team, who attempted it second, managing to cover nearly the whole surface with their novel 3D printed pavers onto fabric, enabling them to roll it up and then deploy it as an individual sheet or a blanket. Let's see how the Polish innovative solution of a stacked interconnected sheets plays out. And keep in mind, they're trying to do this task on a tight time limit, as well as trying to clear the 5 pieces of debris out on the field between the valley. And not only that, try and beat the score of the other teams who have excavated regolith and deposited it into the hopper, with 40 points up for grabs for the team who deposits the most mass, with other teams being awarded points based on how much mass they deposit compared to that number one team. And the view right now up on your screen, you can see the demonstration of redundant systems firsthand. That scoop at the end of the robotic arm used for excavating regolith can also be used to grab that little notch, that piece of string, to unfurl the pavers. And this is showcasing how some systems, when you design them, it is best to have redundant or secondary uses. So one of the demonstrations of this is there was a PhD student working in NASA Ames who taught me how to code in basic Python, thank you. She was working on how to use a rover wheel that got jammed in an awkward position, how you could use that to excavate the surface and also clear a path for a tiny little baby rover to drive safely through dangerous terrain. And the rover team's making good time here. Let's see if they can unfurl the rest of their paver system. It's taken them 7 minutes so far. And the objective for this activity, for those who are wondering, is to cover that blue spray painted area, 1.2 by 2 meters, with pavers to demonstrate a dust mitigation technique of building a road on the lunar surface. And if the Polish team can unfurl these pavers to cover that area, they are awarded points based on how many pavers are in full contact and within the boundaries of that area. And just showcasing how even in space, zip ties and duct tape are useful for everything. It looks like that little loop is in fact a zip tie. And I can tell you, you can do a lot with zip ties under pressure, as the rover I used to work on was held together by zip ties in a dream when we were competing. There it is, Project Scorpio unfurling their pavers as they attempt activity number 4. Of course, they don't have to complete these activities in any sequence. If they successfully cover this area with pavers, they may be able to nab all 35 available points if they manage to do it within the boundaries of that designated zone. But so far, it's looking pretty good. And a phenomenal effort by the team, managing to deploy and unfurl a sheet of their pavers being held by the robotic arm loosely on the rover. Huge effort. Testament to just how well their operators know their system and how much they've trained with their system to be able to do those complex movements so smoothly under pressure of the competition environment. So my hat's off to them. It looks like now they're moving on to the excavation and deposition task if they go left, or potentially they may be readjusting their pavers. And I remind you, you are only awarded points for all the pavers that remain within the boundaries of that rope, within a buffer, of course. And if the pavers have complete contact with the ground, and it looks like their approach is to try and grab those teeth in between the joints of the pavers and drag it across just laterally. Really novel approach to this difficult challenge. Not only does the team have to design and develop these pavers within the constraints, they need to carry them over, deploy them, readjust them, and then last but not least, drive over the road to demonstrate that it works. And they'll be awarded points based on the position of the pavers at the end of the task. The team has about 25 minutes left on the clock with the end time at 4:10 p.m. They're making excellent pace, trying to realign these pavers to be within the boundaries, demonstrating some excellent rover manipulation using that robotic arm with the end effector, or the end piece being that scoop with metal fingers. And you can see just how effective that fabric on the tires with the huge wheelbase, lots of spread out forces, demonstrating just how excellent the advantage and disadvantage of different approaches are for for something as simple as a wheel. And the rover has excellent maneuverability across this course, consisting of very loose sand, trying to simulate the lunar surface, which consists of finely crushed rock called lunar regolith, and it behaves very uniquely, I should say, with some excellent photos of the Apollo astronaut boot prints almost permanently preserved in the extremely fine-grained regolith. Because it's so fine-grained and so angular, and there's no wind on the moon, the ultra-fine-grained portion of the regolith, the dust, manages to capture extreme resolution, so you can see the exact corners and edges and logos of every boot print, every feature left on the moon by the Apollo astronauts. And this material is extremely loose on the surface, and if you dig just a few centimeters below, what happens is the material becomes extremely dense, so dense in fact it is more dense than the material that we can compact here on Earth on construction sites. It behaves like concrete, even though it is just loose sand that gets compacted with time. With just 15 minutes passed into the task, the Project Scorpio team, all the way from Poland, are showcasing some of their expertise in international teams coming in and driving over its own road. Fantastic effort. And now it looks like the rover is going to progress on to clearing out the debris from that valley, worth 20 points, with each piece being awarded once that piece is removed from the allocated area, spray painted in blue. And depending on the time remaining, they will then attempt the excavation deposition task, consisting of moving the pile of regolith, or as much as they can, into the hopper, with teams being awarded points for the amount of mass that they deposit. And let's see if that robotic arm has yet another use. That scoop can deploy pavers, move them, pick up debris, and excavate regolith. Showcasing how one single robust system, like a well-designed and well-understood robotic arm, can perform many tasks. And this is the essence of space exploration: is many things that you send into space, many instruments, and many aspects of any moving system or mechanical system must have redundancies in case something goes wrong, as well as several applications that can be used with it. You have played in a playground of the big Tonka excavator trucks. I imagine that's what it's like for them, only this time they're doing it through laptops and communicating it wirelessly to a huge, complex lunar rover. And I'll remind everyone that these systems are designed and built by undergraduate and sometimes postgraduate students, but largely undergraduate, in the spare time they have when they're not studying or potentially working. And again, these systems, no one tells you how to build a lunar rover or a Mars rover at university. You have to take the fundamentals that you learn in lectures and workshops, the experience that you garner from listening to your lecturers and talking with your other students, and then taking those skills forward into designing, testing, and integrating your own rover, and then deploying it here at the Australian Rover Challenge, and taking all the failures and mistakes as lessons onwards into future years, redesigning the rover and getting it better and better every year. And we can see that in action as the Polish team continue to very smoothly progress their way through this arena and through this course, showcasing the accumulation of several years of expertise, practice, long hours testing, long hours fixing, more and more debris being cleared. With just about 20 minutes left on the clock, the Polish team are methodically making their way through each task, clearing out the debris very precisely from this marked area, with plenty of time left over to see how much regolith can they put into that hopper to try and take home those points off of Monash Nova Rover, who were the first to deposit a significant amount of regolith into that hopper. Let's see how much time they can play with that little scoop. Looks like through that feed on the base station, the operator is controlling the arm through a keyboard. Just a testament to the fact of how much training and practice they've done with this system. Many teams have controlled their rover in a variety of different methods. Some of them use joysticks, some of them use Xbox controllers, some of them use keyboards. Some of them even use virtual reality headsets to view from the rover's perspective to get that camera feed through. Really, anything that works best for your team is the technique or method that you should use, and you find that from testing. And it looks like this is definitely paying off for the Polish team with about 18 minutes left on the clock. And you'll see on the live stream now, it looks like they've just snapped off the end effector of their wrist. This, ladies and gentlemen, is a demonstration of when things go wrong, what do you do as a team to recover? And with just about 15 minutes left on the clock, let's see how Project Scorpio recover from this incident. They're sitting very well, having secured almost up to 35 points as part of their construction task, 5 points from descending down the ramp, almost a maximum of 20 points of clearing the debris, with 40 points on the table for excavating and constructing. Sorry, for excavating and depositing the regolith. And for those tuning in for the live stream for the first time and those new spectators out here on the pitch, you are witnessing currently the Polish team from Wrocław with about 15 minutes, just under 15 minutes left on the clock, competing in the excavation and construction task of the third installment of the Australian Rover Challenge. Just up there on the screen, 14 minutes 30 left. They've just completed the construction task where the rover had to deploy its own pavers. They managed to clear 4 pieces debris out of the 5 available pieces, scoring about 15 out of 20 points. And it looks like they're trying to slowly nudge that last piece out of the arena using what's left of their wrist. Really nail-biting finish here, trying to get as much as they can done with having just snapped off the end effector of their wrist. But they were just showcasing how a simple scoop at the end of their wrist was not only able to deploy and readjust their pavers, but clear debris and also be used for excavation and deposition. Truly a novel demonstration of redundancy. There's the finish line, that blue mark. If they just get that piece over that line, they'll be awarded the remaining points out of 20 points for clearing debris. Ever slowly but surely, they'll be nudging that piece with the broken remnants of their wrist. Absolutely phenomenal effort from the Poles. About 13 minutes left on the clock. Let's see what they will do. They've got a few options ahead of them. They can either end the task, try and recover and pick up what's left of the scoop, and try and excavate regolith. Let's see what they do. And not wasting any time, the rover's making its way potentially towards the RAS, the regolith acquisition zone. And this is a task that the future Australian, fully Australian Trailblazer mission will do as part of a foundational services rover sent to the moon together with NASA's Artemis program in the Moon to Mars initiative, aiming to put the first woman and next man back on the surface of the moon, but this time to stay. And it looks like the rover is coming to greet the rest of the field team to say hello. And let's get a huge round of applause for the Poles here. Absolutely phenomenal effort. Truly demonstrating extreme operator training, perseverance against all odds. Phenomenal effort with 11 minutes on the clock. As Project Scorpio has finished quite early, the next team and the last team for today's excavation and construction task is the University of Adelaide with a start time of 4:15, end time of 4:45. Once again, let's get a round of applause for the Polish team all the way from Wrocław. Huge effort. Congratulations. Go and get that broken wrist.
Australia is a nation of creators, aviators, protectors and innovators. From aviation's first light to the dawn of the jet age and beyond, at Boeing, we're building the future together here in Australia. Inspiring those in pursuit of new frontiers, connecting, protecting and exploring our region and the world. Home to the broadest aerospace portfolio in Australian industry, powered by talented, dedicated and diverse teammates. Delivering manufacturing excellence, building composite aircraft parts for the world's most efficient airplanes, using advanced robotics, materials and digital technologies. Never compromising on safety or quality, always focused on sustainability. Solving tomorrow's problems today with Australia's leading researchers, scientists and universities. Developing new military platforms and communications networks and helping ensure they are always mission ready. Keeping customers airborne by providing the services they require. We stand shoulder to shoulder with Australians during natural disasters, on the front line and in peacetime. We support veterans and our community, and we nurture the next generation of aviators to excite, to be bold. Boeing Australia. Made in Australia by Australians for the world.
Okay, are you ready? The first university to admit women, 2 Nobel Prizes, then another, then a couple more, 12 knighthoods, 22 Olympians, a pack of COVID-sniffing canines, Australia's first female Prime Minister. Finally, treatments for diseases and other scary things, the first female Queen's Counsel, Supreme Court Judge and State Governor, all in one, first in the family with a degree, a black belt, a robot. First Aussie to walk in space, helped detect gravitational waves, made lots of babies, world top 100 in all this stuff. Launched a satellite, revived lost languages, home to 1600 brainiacs, and a winery, all in the heart of Australia's most livable city. So, what's next? Make history at the University of Adelaide.
Currently up on screen with a time at 4:12, start time at 4:15, the University of Adelaide rover team, their rover right there, pictured up on the lander with a huge, monstrous scoop at the back, or what seems to be the front. It looks like they'll be reversing down the lander with their antenna right next to the large red and yellow E-stop. Their allocated task time is 4:15 to 4:45, and this team has really gone against all odds. Just over half their team out of the count because of COVID, so they're running on a skeleton crew. They're really pushing the performance of their rover. With the start time at 4:15, or should I say the allocated time at 4:15, the field and base station team are currently still in the setup time, where they can freely communicate using the walkie-talkies available to them to make sure that the rover is functional and operational before they tell the judges it is start time. The moment that start time is initiated, the field team must vacate the lunar surface and the base station is sealed, meaning, much like on Earth, the only information that base station team receives is the feed from the cameras and the communication to the rover's brains, the computer, oftentimes a NVIDIA Jetson. This highlights the real-world scenario of when these students may one day work on a real lunar rover, that you can't simply send a technician to go repair things, to go unbug it. You need to design your system so that it is robust and can overcome any hurdle or challenge thrown at it. And one of those big hurdles that all the teams are facing today and yesterday is this loose sand that covers the arena. And this is a real-world problem that every human astronaut or rover is going to have to encounter and face on the lunar surface. Because unlike sand, the lunar surface is covered by a loose, fine, crushed rock called regolith, and this regolith gets everywhere, gets into everything, is extremely loose, hard to predict, and also, interestingly, becomes extremely hard as all the particles are packed together tightly with just a few centimeters beneath the lunar surface. And with that, you can see on the screen the official start time, 39 minutes, 45 seconds into, or remaining for the task, for the last competitors of the third installment of the Australian Rover Challenge excavation and construction task, proudly supported and sponsored by some of the lovely sponsors you can see up on the screen, including the premier sponsor Boeing, who have sponsored the mapping and autonomous challenge that will take place on Sunday, as well as iSpace supporting the space resources task on Saturday, and the Australian Space Agency, who have supported the post-landing task, which we had yesterday, on Thursday. I'd like to remind everyone that later today we have, as part of the University of Adelaide Make History Speaker Series, Writing History in the Stars, we'll have John Coulton joined together with Dr. Kimberly Clayfield from CSIRO, Dr. Sarah Cannard from Nova Systems, and Dr. Matthew Tetlow from Innovor to discuss how space science is addressing humanity's greatest challenges using satellite imagery. And this will be a free and public event over in the Braggs Lecture Theatre, just next to the Challenge Arena here at 5:30. Doors opening at 5. If you're interested in space and want to learn more about how we can use satellite imagery to track natural disasters like bushfires and flooding, but also to improve the efficiency of agriculture, such as where and when do we spray pesticides, or even if we need to use pesticides, as well as optimizing the crop rotation and farming of crops out in Australia and in other countries, of which crops are ready to harvest and when. Together, satellite imagery is extremely useful for also tracking the migration of coastlines and raising sea levels that help us track the status of climate change as it takes place on our beautiful Earth. But away from Earth and onto the moon, 37.5 minutes left for the University of Adelaide excavation and construction task. And at 4:20 p.m, we are 5 minutes into the allocated task time for the University of Adelaide rover team, completing the excavation and construction task. And it's taking its first steps now down the lander with 5 points up for grabs once all 6 wheels make contact. Huge round of applause as they're moving with plenty of time to spare. Once all 6 wheels make contact with the ground, they are awarded 5 points for activity 1, descend down the lander ramp. And then it is up to them to choose in what sequence and to what extent they complete each of the activities, which can include debris clearing. And there they go, off to a sensational start. As I was saying earlier, debris clearing for 20 points, excavation and deposition for 40 points, and construction for 35 points. And altogether, these activities are meant to demonstrate a foundation services rover, or what activities a foundation service rover would have to complete on the lunar surface to try and simulate the tasks that an Australian rover will have to complete in the not so distant future as part of the Australian Trailblazer mission, as Australia's ongoing collaboration with NASA and space agencies around the world, including the DLR and ESA. As part of our contribution of a Foundation Services rover to demonstrate the excavation and deposition of regolith from the RAS, the regolith acquisition zone, and some amazing pivot steering there, individual rotation for each wheel, and an incredible display of control, and that is the product or accumulation of, I'm guessing, countless hours of restless nights. And that large rotating barrel drum looks like it's ready to devour some regolith. And as it progresses up towards the north side of the arena, towards the crater, which will be the location of tomorrow's task, the iSpace Space Resources task, where rovers will have to excavate icy regolith and then deliver it to us as extracted water. And this is a real-world scenario that rovers will have to complete in the not-so-distant future to demonstrate that we can, in fact, extract water from the lunar surface at the poles. And water is, of course, incredibly useful out in space, as it is extremely heavy, relatively, to launch into space. And that's why the astronauts up at the ISS have extremely efficient ways of recycling water. And as the saying goes, today's coffee is tomorrow's coffee. And for those joining us on the live stream and the new spectators out on the pitch, welcome to the University of Adelaide rover team's attempt at the excavation and construction task as part of the Australian Rover Challenge, our third year here out at beautiful, partially sunny Adelaide. With 30 minutes left on the clock, the rover has successfully descended down the ramp and achieved 5 points, and looks like it's trying to rotate on the spot to try and enter that debris clearing area where 20 points are available up for grabs. And if anything goes wrong, we have two contingents. We have the base station team, who are currently tucked away in a base station just behind the bleachers here, inside a tent where the only information they're receiving is that through the rover, so the camera feed and the sensor data coming from the rover transmitted wirelessly, or should I say via radio. If anything goes wrong, they can call for an intervention where the field team, comprising a field crew, can intervene and perform some basic maintenance operations on the rover. However, By doing this, they take a 10% haircut to the available points for this task. And if things go really wrong, the field team can hit that E-stop, which is the large red and yellow button on the back of the rover, ceasing all power to the rover and immediately ending the task. And we can see now that rover bulldozer at the front of the rover successfully rotating and pivoting. Again, that fantastic demonstration of the rover wheels and control. And for those present here today, I'll just remind you of the Make History speaker series, Writing History in the Stars, hosted in the Braggs Lecture Theatre, just next to us here at the Challenge Arena, starting at 5:30, doors open at 5. John Coulton will be joined by Dr. Kimberly Clayfield from CSIRO, Dr. Sarah Carnard from Nova Systems, and Dr. Matthew Tetlow from Innovor to discuss how space science is addressing humanity's greatest challenges using satellite imagery. Again, this is a free and public event, and I'll also remind you of Mini Mammoth Games, just on the other side of the arena, to the left, inside Ingani Wardley, who have developed a game mimicking the exact rover and prop layout here you see today, which is a game that you can go and play and interact with right now. So if you want to be part of the Rover Challenge and participate yourself, go check out Mini Mammoth Games, just next to the cafe in Ingani Wardley. And up on the screen right now, you can see the University of Adelaide's rover with that rocker bogie suspension, individual pivot steering for each wheel. Each wheel looks like comprised of a 3D printed central red circle with a flexible filament as the wheel tread. Circle? Yeah, it's a circle. And that flexible filament allows the rover wheel to depress as it traverses across the surface, increasing the amount of surface area in contact with the surface, potentially providing more traction. And that rotating object is, of course, their scoop, mimicking that of NASA's RASOR rover, the RASSOR rover, developed over at Kennedy Space Center in their large Big Bin, which is essentially a large glass room filled with real regolith simulant, which means finely crushed rock, so fine that if you want to work inside that Big Bin, you need they call them bunny suits, which are large almost like hazmat suits to prevent the dust getting onto your skin, and a very serious respirator to prevent the dust getting into your lungs. And in this environment, they test things prior to deployment onto the lunar surface. And today out here, we've got a regular simulant, but it's much simpler and much less effective, much more safe, in fact, is just regular sand. However, this sand is still proving to be a huge issue for many of the rover teams, getting bogged down and losing traction or getting stuck in this loose material. And with just under 25 minutes left on the clock, University of Adelaide have achieved 5 points so far, with 3 activities remaining for them: the clearing of debris, the construction of a road using pavers designed and built by the students, and last but not least, the excavation and deposition of regolith from the RAS, the regolith acquisition zone, into the hopper connected to the post-processing plant down in the bottom left of the field. 15 minutes left on the clock. The Rover team from Adelaide is moving once again. Moving into the light, out of the shadow. The Rover is on its way through the extreme terrain of those tiny little hills and rocks, taking the path least traveled by all rovers for this task, on its approach to the RAS. 13 minutes left on the clock. Still many points available to the team if they manage to maneuver their way through that extreme terrain. And down here at the Australian Rover Challenge on this simulated lunar surface, these features are very much like the features you would find on the lunar surface, if not a little bit more easy to navigate, as the lunar surface is covered with large hills, large rocks, loose sand, everything that a rover would fear. However, the rovers today have demonstrated an extraordinary capability of overcoming any hurdle that they're faced with, and with 12 minutes left, I'm sure the Adelaide team can find their way out of this pickle. Right near the RAS, all they need to do is get a little bit of regolith from that designated area and deposit it into the hopper to be awarded points. And up on the screen now, you can see those 6 wheels. And this raises good questions of how many wheels should a rover have? What does the suspension look like? How big are those wheels in terms of the depth? A good rule of thumb is the diameter of the wheel, the size from the top to base, is about double the size of the obstacles you can drive over. So if the obstacle is bigger than half the diameter of the wheel, sometimes that obstacle just may be too big. But depending on how your chassis and suspension work together with the other control systems, sometimes different approaches can overcome even big hurdles. And it seems like the field team have called for an intervention, as the field team and base team are currently in discussion over the walkie-talkie to figure out the current position, orientation and situation of the rover as it is stuck up on this hill. 10 minutes left. Can they free themselves? Just about a meter away from that RAS. And that bulldozer is primed to excavate and deposit the regolith. Intervention teams may slightly adjust the position of the rover. As part of this, they'll take another 10% haircut to the total available points to them for this task. The rover is moving once again. However, if it moves over the edge of that boundary, it's instant disqualification. And there goes the wheels, once again pivoting. Just over 8 minutes left. Feasibly plenty of time to score some points as part of the excavation and deposition task. Up to 40 points available. Perching itself up on the RAS, that bulldozer scoop ready to sink down and pick up some regolith. Just meters away from the hopper. Just under 7 minutes left. So many points available to them right now. So it looks like the rover's being controlled by an Xbox controller. As with all teams, every team has a novel way to control their rover. Some use Xbox controllers, some use joysticks, some use keyboards. There's really no right or wrong answer as long as you are efficient and well versed in how to use your rover. Really, any technique is valid as long as it works. With just under 5 minutes left, a brief reminder of the Make History speaker series, Writing History in the Stars, which will take place at 5:30 today. Doors opening at 5, so just in about 10 minutes. And here goes the Rover on its approach to the hopper. Congratulations to the University of Adelaide Rover team as the last competitors of Day 2 of the Australian Rover Challenge, with 8 teams competing in the excavation and construction task. Thank you everyone for tuning into the live stream and spectating out here on a gorgeous Adelaide day. Tomorrow, the fun doesn't end. We have the iSpace Space Resources task starting, of course, at 9 a.m. Teams will be tasked with excavating icy regolith from the lunar surface and then processing it in situ to extract liquid water to be given to us, the judges, where they'll be awarded points based on the mass of liquid provided, as well as how they respond to questions in a space resources presentation, where they explain how the system works and how the data they collected is valid. And of course, on Sunday, the Boeing mapping and autonomous task, where the rover is expected to semi-autonomously and autonomously navigate the surface and identify the location of every piece of infrastructure. And right now, up on the leaderboard, you can see the top three, Project Scorpio and Unimel, battling it out for second and third. Monash Nova Rover from Melbourne in first place with a comfortable lead of 250 points. There's still a lot of room for upset in the next 2 days. 200 points available to teams. I look forward to you joining us for another lovely day of the Australian Rover Challenge, and I hope you have a lovely evening. Goodbye.
Australia is a nation of creators, aviators, protectors and innovators. From aviation's first light to the dawn of the jet age and beyond, at Boeing, we're building the future together here in Australia. Inspiring those in pursuit of new frontiers, connecting, protecting and exploring our region and the world. Home to the broadest aerospace portfolio in Australian industry, powered by talented, dedicated and diverse teammates. Delivering manufacturing excellence, building composite aircraft parts for the world's most efficient airplanes, using advanced robotics, materials and digital technologies. Never compromising on safety or quality, always focused on sustainability. Solving tomorrow's problems today with Australia's leading researchers, scientists and universities. Developing new military platforms and communications networks and helping ensure they are always mission ready. Keeping customers airborne by providing the services they require. We stand shoulder to shoulder with Australians during natural disasters, on the front line and in peacetime. We support veterans and our community, and we nurture the next generation of aviators to excite, to be bold. Boeing Australia. Made in Australia by Australians for the world.
Okay, are you ready? The first university to admit women, 2 Nobel Prizes, then another, then a couple more, 12 knighthoods, 22 Olympians, a pack of COVID-sniffing canines, Australia's first female Prime Minister. Finally, treatments for diseases and other scary things, the first female Queen's Counsel, Supreme Court Judge and State Governor, all in one, first in the family with a degree, a black belt, a robot. First Aussie to walk in space, helped detect gravitational waves, made lots of babies, world top 100 in all this stuff. Launched a satellite, revived lost languages, home to 1,600 brainiacs, and a winery, all in the heart of Australia's most livable city. So, What's next? Make history at the University of Adelaide.